Hey guys, can you all hear me? Am I audible, visible? I think yes. So what's up, people? How are you all doing? How are you all doing? So first of all, I welcome you all again to your Unacademy NEET English channel. I hope all of you are doing amazing. All of you are doing great. So quickly, give us the green signal if we are perfectly audible, visible to everyone. Yes. I believe a lot of students are surprised. What am I doing here? Am I going to teach capacitors? But here on the thumbnail, it's Yawar sir's picture. Yes. Well, the chapter this capacitor, it's not a very big topic. I would say it will not take more than 5 hours to complete with all the theory and problem patterns. Yes. So if you want me to teach it, I can do that. Yeah. Do you want me to start the capacitors? Yes. Do you want me to start the capacitors? Do you want me to do that? Quickly, quickly. Yeah. Guys, I want the same Josh. The Josh with which you started this particular series, with which we started this particular series. I would want the same Josh today also. Everyone. Everyone. The chats should light up. There should be completely the fire emojis in the chats. Yes, that is the aggression which I want from you. That is the aggression which I want from you. Quickly. Quickly, quickly. So, people, you know, today it is day 17. So, till now, we are done with 16 chapters of PCB. And tomorrow, it'll be my session, Chemical Equilibrium, right? Yeah? Promoting my session too. Are you ready for that as well? Are you ready for your most phobic chemistry chapter as well? All right, people. All right. Perfect. Perfect. So I would want you guys to call up all your friends so that Yawar sir can start the session. Yes. By the way, he is not well today. He is not well. He has got cold, cough, etc., etc.
Guys, Wasim sir will be teaching this chapter today, okay? I'll be teaching the next chapter, that is chemical bonding tomorrow, huh? Will that be okay?
Yeah, it's cool.
It's cool. So,
It's chemical equilibrium, by the way. It's not chemical bonding.
okay, chemical equilibrium. So, what's up, people? Is everybody doing great? All of you? So, today we'll be basically killing this entire chapter. I'm not well, but still.
Yeah, he's actually not well. I had to give him a
Okay.
lot of medicine, by the way.
Yes. So, how is everything going in the live chat?
Yes, guys.
How
Show
is
some Josh, yeah. Show some Josh. We will want the same Josh.
Yes.
Show some Josh in the session.
All the people out there. So, guys,
I think it's my time to leave.
yes,
You guys carry on. Wishing you all the luck for this session as well. And be
Yes.
there tomorrow and day after tomorrow, which is going to be the best Christmas gift for all the NEET 2024 aspirants. Right? Perfect. So carry on, guys. Carry on. Take care.
Chalo. Okay, guys. So we'll be basically starting this particular chapter. That is capacitors. Okay. Just a second. Just a second. Okay, guys, so let's basically start this particular session. This is also a very important session. We'll be finishing this chapter. This will not take us much time. So I'll be starting from the scratch and I will be to the point. Okay, all those important points that you need, I'll be telling you, and the theory will be to the point so that each and every problem you would be able to solve afterwards. So let's basically get into this particular session. Let's start with the capacitors, and I will be exactly starting from the scratch. Okay, so listen to me very, very, very carefully. All the people out there in the live chat, okay, stay till the end. Okay, so first and the foremost thing in this particular chapter we will be talking about, that is nothing but capacitors. Okay, what this capacitor is all about. Listen to me very carefully. Let's suppose we have an electrical device fan over here. Okay, let's suppose we have an electrical device fan over here. This is the electrical device, which is a fan over here I have. See, any electrical device, be it fan or motor, anything, or a television, in starting, if you have to start it, it requires high energy, it requires high current. So it is not possible for us to supply that current through a normal wire directly. So what we use this device, okay? That is what we call the capacitor. See, let's suppose I have to start this fan. What will I do? I'll take the wire and I'll plug in the wire so that the current will be sent to this particular fan and it will start basically, it will start. So it is not possible for us to start any electrical device without the capacitor. So we use a capacitor only and only because that capacitor will send the energy to it and then it will start. Sir, why? Because initially, if we have to start any electrical device, it requires initially, it requires, we say high energy. We say high energy or high current. That is only possible with the help of the capacitor. So if you see any fan over there, you'll see the capacitor is basically attached to the fan. Like over here, you can see this is the capacitor, which is exactly attached to this particular fan over here. This is the capacitor. Okay. So now listen to me very carefully. Just a small statement. If you have to start any electrical instrument, initially it requires high energy. So it is not possible to supply this high energy with the help of a normal or regular wire. So we use a device, that's what we call the capacitor. So capacitor supplies the energy to that electrical instrument. So then it starts and then it keeps going. So that is the use of capacitor. We simply say, sir, capacitor is a device. We say it is a device. It is a device which stores energy. Now the question is, why do we need that energy? We need that energy in order to start any electrical device in starting. Okay, I hope this is clear. Now the question exactly is, listen to me very carefully. I'll be to the point. When it comes to the capacitor, every capacitor has a capacitance. Sir, what is a capacitor? Capacitor is a device which stores energy. Why do we have to store that energy? In order to use that energy while we have to start any electrical device. Now listen to me very carefully. We say capacitor has a capacitance. Let's suppose we have a bucket over here. What does this bucket store? It stores liquid, it stores water. We say, sir, this bucket is able to store the water. Now the question is, does this bucket have some capacity? We say, yes, it has some capacity. Let's suppose it is of 10 liters. So means its capacity is 10 liters. How much water it is able to store? Same is the case of a capacitor. When we have a capacitor, sir, this capacitor stores, it does not store water, it stores energy.
and that energy is stored inside capacitor, and we say this capacitor also has a capacity. It has a capacity, and that capacity is what we call the capacitance. How much a capacitor is able to store the charge. More is the capacity, we say more is the capacitance. Less is the capacity, we say less is the capacitance. Is everything clear till over here? Is everything clear till over here? Let me know in the live chat. So we say capacitance is nothing but capacity of a capacitor. How much it is able to store the charge. How much it is able to store the charge. Yes, great. Now, let's suppose I'm taking a spherical capacitor over here. This is a single conductor capacitor, sapphire you say, okay? Now on this sapphire, I'm storing, let's suppose I'll store a charge Q. Okay? Sir, what is a capacitor? It's a device which stores energy, okay? Now every capacitor has a capacitance. Capacitance is how much capacity it has, how much ability it has to store the charge. The ability of a capacitor to store the charge. The capacity or ability of a capacitor to store the charge is called capacitance. Now see, let's suppose I have a sapphire over here. I have a capacitor over here, sapphire or a conductor, whatever you say. And I'm storing a charge Q on it. As I have told you in the last session, if there is a charge, it creates the potential around it. Sir, you have told us, let's suppose if we have a charge Q, at r distance, it has the potential V is equal to KQ divided by R. Okay. And if you increase this charge, this potential would increase. V is directly proportional to the Q. And similarly, I have told you in case of a sapphire, sir, potential is nothing but KQ divided by capital R if the radius of the sapphire was capital R. Now we have over here, in this case, we have a sapphire. And on this sapphire, we are storing the charge capital Q. Now the radius of this sapphire is capital R. Now my question to you is, sir, if I am storing the charge capital Q on this sapphire, is the potential developed over here? Will there be any sort of potential? We say, sir, yes. Because of charge, potential is there. So we say potential is there. Potential will be developed. Okay. So I say if Q is stored on the sapphire, we say V potential is developed. Okay. Potential is developed on the sapphire. Cool. Now, can I say over here, sir, this V is directly proportional to the Q. More you store the charge over here, more potential will be developed. Yes, sir. Now replace this proportionality with a constant. We say, sir, V is equal to over here, or you can simply say, sir, Q is directly proportional to V. Q is directly proportional to V. Just a second. Q is directly proportional to V. Or you might have seen this particular formula. Q is equal to C into V. You can definitely see this formula over here. Sir, what is this C? Where C is the capacitance. Where C is the capacitance of a capacitor. Where C is the capacitance of a capacitor. Sir, we say sapphire over here, we are storing Q charge on it. Sir, because of Q charge, potential is being developed. Now my question to you is, Q is directly proportional to V over here. Sir, if we store more charge, more potential will be developed. Now we say Q is equal to C into V. And from over here, can I say this C is equal to Q divided by V? And this is what we call the capacitance over here. Capacitance is simply the capacity of a capacitor. Sir, does that mean this capacitance depends upon the charge? No. Sir, does that mean this capacitance depends upon the potential? No. Capacitance is a constant. It is how much ability a capacitor has like we have a bucket. I told you we have a bucket. It is having the 10 liters of capacity. If you store more, if you keep on storing the water, its capacity will remain 10 liter only. It does not depend upon the amount of water you store over here. Same is the case in this one. Same is the case in this one. If we store the charge on this sphere, sir, because of the charge, potential is developed. We say they are proportional. But when it comes to the capacitance, this capacitance is a constant of proportionality. This is constant. Its capacity will remain same. As simple as that. Is it clear to each and everyone till over here? Let me know. Is it clear to each and everyone? Is it clear? Give me a thumbs up. Great, great. Let's move on to this one. Capacitance of a single capacitor. What does capacitance of a single capacitor mean? Listen to me very carefully over here. Let's suppose single capacitor or single conductor means we have a sphere over here. Let me take a sphere over here. Okay, this is a sphere. And on this sphere, we have a charge Q. Let's store the charge Q on this particular sphere. Okay. And the radius of this sphere is, let's suppose, R. Radius of the sphere is, let's suppose, R. We say, sir, in this particular case, as Q is equal to C into V. Q is equal to C into V. Sir, because of the charge, potential is developed on the sphere. And we know, sir, if we are storing the charge on this capacitor, means this capacitor has the capacity. It has some capacity. It has some ability to store the charge. So we say that capacitance is C. That capacity is C. So we say Q is equal to CV. Now over here, can I write its capacitance? You say, sir, C is equal to Q divided by V. Yes, yes, yes. What we are supposed to do is that we have to find its capacitance. How much capacity it has to store the charge. Now listen to me. We say, sir, as we know, see, at R distance, I have told you previously, if we have a sphere and on that sphere Q charge is present, at R distance, what is the potential developed? You say, sir, on the sphere, we know, sir, on the sphere, we know potential at surface is nothing but K Q divided by capital R. This charge is stored on its surface. So we say in this particular case, sir, potential will be how much? V is equal to KQ by R. Now, can we put this potential over here? You say, sir, C is equal to Q upon, and instead of this V, I'll put K, this Q divided by this R. Q and Q will get cancelled out over here. So this will be R divided by K. Can I just write over here? This C will be nothing but R. And what is the value of K? We know value of K is 1 by 4 pi epsilon naught. So I'll put up over here 1 upon 4 pi epsilon naught. Can I take this in the numerator? So we say C is equal to 4. We can write this something like this, 4 pi epsilon naught R. So we say this is the capacitance. This is the capacitance of a single capacitor or single conductor or spherical capacitor, whatever you call it. Okay, that is C is equal to 4 pi epsilon naught R. So from this you can clearly see that this capacitance does not depend upon charge. It depends upon the dimensions. It depends upon this material. I hope you got it. Is it clear to everyone? Is it clear to everyone in the live chat? Is it clear? Shall I repeat anything? Okay. So till now, the capacitor is a device which stores the energy. Why do we have to store the energy? In order to use that energy when we have to start any electrical instrument. Then capacitance. What is capacitance? It is nothing but the capacity of a capacitor. How much energy we can store in a capacitor, that is its capacitance. Then we have capacitance of a single capacitor, that is 4 pi epsilon naught R. Now this is a common question that you face in the exams, which is very important, Now see, I'll make you understand what this is all about. See, what is given is that we have got n number of small capacitors. From here, the numerical part starts, okay? So we have got n number of small capacitors, or even in some books you may find it that they call it small drops. So we say these are the small n capacitors of which is having the charge small q, small q charge, n number of small capacitors. And if we combine these n number of small capacitors, it forms a big capacitor. And let's suppose the capacitance of this small one capacitor is C, and the charge stored inside this is Q, small q, and potential on this is V. If there is charge, there is potential. This small capacitor has capacitance C. It has, we say, potential V. It has charge Q, and it has, let's suppose, this radius is R, small r. Now, once we combined, we say how many capacitors are these? N number of capacitors. So we say n capacitors combined to form a big capacitor. N capacitors are joined together to form a big capacitor. Now, this big capacitor has different capacitance, let's call it C dash. It has new potential developed, let's call it V dash. It has big radius, let's call it R. And it has new, we say, charge on it, that is capital Q. Now, what they can ask us, I'll be showing you what are the questions they have asked previously. What they can ask us is that find the new capacitance of this big capacitor, find the new voltage of this big capacitor, find the charge on this big capacitor, find the radius of this big capacitor. They can ask these questions. Listen to me very carefully. Will not go in much detail. I'll be telling you, just remember this trick and you can solve each and every single question. The first thing is, if n capacitors are joined to form a big capacitor, if they ask you to find what is the value of this Q, how much will be the charge on this big capacitor, you say, sir, this Q will be n times of small q. This Q will be n times of small q. Remember this. Is each and everything crystal and clear? Is each and everything crystal and clear? And if they ask you, what is the value of this radius? What is the radius of this big capacitor? You say, sir, this R will be n raised power 1 by 3 into radius of small r. The radius of big capacitor will be n raised power 1 by 3, the radius of small capacitor. If they ask you to tell me what is the potential developed on this big capacitor, you say, sir, this V dash will be, that is simply n raised power 2 by 3 into V. N raised power 2 by 3 into V. What is N? N is the number of small capacitors. And 2 by 3 and V. What is V? V is the potential on the small capacitor. And if they ask you what is the capacitance of this big capacitor, so sir, this C dash will be n raised power 1 by 3 into this C. C is the capacitance of this small capacitor. These are the 4 questions they can ask you in this category, and that's it. They cannot ask you beyond this. If you have n capacitors joined to form a big capacitor, what is the capacitance of the big capacitor? That is this one. What is the voltage of this big capacitor? That is this one. What is the radius of big capacitor? That is this one. What is the charge on big capacitor? That is this one. And the question was asked in NEET 2021 on the same concept. See, in this case, 27 drops of same size are charged. Over here, we are given 27 drops. So means N in this case is 27. 27 drops or capacitors are combined together to form a big capacitor. So 27 drops are combined to form a big capacitor. Okay, they form a bigger drop. Calculate the potential of the bigger drop. We have to calculate the potential of this bigger drop. Let the potential of this bigger drop be V dash. And the potential of smaller drop is V. Sir. If n capacitors are combined to form a big capacitor, what is the potential of the big capacitor? V dash is equal to n raised power 2 by 3 into V. Use the same formula over here. Sir, the potential of this big capacitor is nothing but V dash is equal to n raised power 2 by 3 into V. And V is given, that is 27 drops of small same size are charged at 220 volts. Means V is equal to 220 volts. Now we say over here V dash is equal, the value of n over here is, that is 27. This is 2 by 3, and instead of V you will put 220. Now see 27. Can we just write it something like this? This will be V dash is equal, this is 27, and we can write it something like this, 1 by 3 into 2. So now this is cube root of 27. So you say this is cube root of 27. You say, sir, this is nothing but 3 into 3 into 3. Okay. That is how much? We say 27. So we say that is nothing but 3, and this will be square into V. So V dash will come out to be, that is 3 3 is 9 into V. So this will be 9 into, what is the value of V? That is 220. So how much it will be? This will be 0.819 volts will be the potential of this big capacitor. Is it clear to each and everyone? Let me know in the live chat. Let me know in the live chat, guys. Show some fire. Yes. Okay, great, great. Is it clear to each and everyone? Yes, great. Simply, if you are given n number of capacitors to form a big capacitor, they ask you to find the potential, capacitance, radius, charge. You can find each and everyone. I have given you the trick. That's it. Great. Let's move on to the next one. Now in this question, 64 small drops of water whose charge and radius are same. In this case, 64 drops are basically given. Okay. Now in this particular case, n is equal to 64. 64 drops are joined to form a big drop. Okay. Let's suppose the capacitance of these small drops is C. And in this case, we are supposed to find the capacity of the big drop. We have to find C dash. And I have told you, come over here. If you have a capacitor and n number of capacitors, we say in that case the capacitance will be C dash is equal to n raised power 1 by 3 into C. Can we use the same formula over here? Sir, these capacitors 64 are joined to form the big capacitor. How to find the capacitance of this one? We say, sir, this will be C dash is equal to n raised power 1 by 3 into C. So we say this C dash will be n. What is the value of n? That is 64. And this will be cube root 1 by 3 into this C. And this will be how much? That is 4 times of C. So C dash will be 4 times of C, means it will be 4 times. I hope each and everything is crystal and clear. Great, great, great. Now comes basically the question, that is parallel plate capacitor. Yes. See, previously I told you a single capacitor, or we say a spherical capacitor. Sir, this is the spherical capacitor. Let's suppose I am storing the charge Q on this spherical capacitor. Yes, sir, I'm storing the charge Q. I'm storing the energy. You say charge, energy, it's one and the same thing. Okay. Now over here, sir, this charge, this energy is not bounded over here. This is not bounded. What I mean to say over here is that this energy is not safe. Energy is not safe here. We say energy is not safe here. Why? Because see, this, if I let's suppose place one more capacitor over here, now the energy is between these two capacitors. Now I can say energy is bounded. But this is not the situation. In case of a spherical capacitor, or single capacitor, you store the charge over here. So it will be something like this. Energy is from this surface to infinity. So we say energy is not safe, energy is not bounded. There are high chances that this energy, this charge may leak from this surface. I hope you are getting my point. Yes, sir. So what we do is that we discovered or we invented another capacitor. That's what we call the parallel plate capacitor, in which energy is safe, Let me basically make the parallel plate capacitor over here. Let's suppose we have a plate over here. Okay, let me make another plate over here. This is another plate over here. Yes, sir. Now, in this particular case, this is one plate and this is another plate. Can I say over here, these two plates are parallel to each other? Yes. And this is what we call the parallel plate capacitor. And over here, we can see clearly that distance between them, let's suppose this is D. This is the separation between the plates. And area of the plate is A. So means from now onwards, if you have to make the parallel plate capacitor, you take one plate something like this and you take another plate something like this. Now they are parallel to each other. Distance between, there is some separation between the plates. This combination is what we call the parallel plate capacitor. We say when two plates are placed parallel to each other and has some separation between them, it is called parallel plate capacitor. So it is called parallel plate capacitor. I hope this is crystal and clear to each and everyone. So how do we make the parallel plate capacitor? Place two plates parallel to each other, it forms the parallel plate capacitor. Now, in this particular case, sir, if there is a capacitor, that capacitor stores the energy, means it has capacitance, it has capacity. Now, the capacitance of parallel plate capacitor, to find its capacitance, we have to find its capacitance, how much charge it can store. We say, sir, it is nothing but C is equal to epsilon naught. What is the area of the plates? We say A divided by, what is the distance between the plates? That is D. Separation between the plates is D. Epsilon naught A divided by D is the capacitance of the parallel plate capacitor. Now you say over here, sir, is the energy safe over here? Is the energy bounded over here? Yes. We say energy is stored between these two plates. Energy is stored between these two plates. Okay. I'll show you after some time. Energy is stored. It is bounded between these two plates. There are no chances that the energy will leak over here. So that's why this is a good capacitor when we compare it with the single capacitor. Is it clear to each and everyone? Is it clear to each and everyone? I'll make the positive and negative plate after some time. Wait for some time. Yes. So capacitance of a parallel plate capacitor is what? Epsilon naught A by D. Capacitance of a single capacitor or the spherical capacitor is how much? C is equal to 4 pi epsilon naught R, where R is the radius of this sphere. Is it clear? Is it clear? Any sort of doubt? Great. Now, this was the question which was asked in NEET 2022. If the area of a plate is halved and the distance between the plates is doubled, then find new capacitance. See, we are given a capacitor over here. This is a parallel plate capacitor. Okay. The area of the plates is A. Distance between the plates is D. So the capacitance of this is epsilon naught A divided by D. Yes, sir. Now, the questioner says that if the area of the plates is halved, now what we do is that we'll take the same capacitor and we'll make the area of these two plates as A dash is equal to A by 2. Area is halved. And since distance between the plates is doubled, this distance initially it was 2D. Now it becomes, sir, that is 2D. Can you tell me what is the capacitance finally? You say, sir, finally capacitance will be C dash is equal to epsilon naught. See, capacitance of a parallel plate capacitor is epsilon naught A by D. What is A over here? That is A by 2. So instead of A, I'll write A by 2. And A by D. Instead of D, what is D over here? You say, sir, that is nothing but 2D. Yes. So we say this C dash is equal to epsilon naught A divided by 2 into 2 is 4D. Now you tell me one thing. Epsilon naught A by D. Epsilon naught A by D. That is C. That is the capacitance initially. So we say this C dash is equal to, instead of this, I'll put C divided by 4. So we say in this particular case, this capacitance decreases by 4 times. Yes, 1 by 4 or C by 4. Is it clear to each and everyone? Great, great. Guys, show some fire in the live chat. I want you guys to show some fire. Gopika Shri is saying, please call my name, okay? That's your name. Shall we move forward? Yes. Another question on the screen. Can you guys solve this particular question? Great, great, great. Okay. These fire symbols basically boost my energy. I'm not feeling well today. I'm having cold, cough. It's very cold over here in Kashmir also. Cool. Now see, the question says that the capacity of a parallel plate condenser, sometimes they will ask you capacitor or they'll write condenser. It's one and the same thing. Is 15 microfarad. Given we have a capacitor over here or a condenser over here, we have a capacitor over here, okay? Let's suppose we have a capacitor over here. It is saying that its capacitance is nothing but 15 microfarad, okay? So we basically measure the capacitance in farad. It is given in microfarad, okay? When the distance between the plates is 6 centimeter, when it is 6 centimeter, so it is saying that the distance between the plates is nothing but D is equal to 6 centimeter. Its capacitance is 15 microfarad. Now afterwards, this is initially. Then what it says, if the distance between the plates is 2 centimeters, then it says that if we decrease the distance between the plates, if we make it something like this, means finally, if we decrease the distance between the plates, and if we make it D is equal to 2 centimeter. Initially it was D is equal to 6 centimeter and finally it is saying D is equal to 2 centimeters. Now in this case, it is saying what will be the capacitance. If we have a capacitor, parallel plate capacitor, its distance between the two plates is 6 centimeter, its capacitance is 15. Now if we decrease the distance from 6 to 2, what will be its capacitance? Area of the plates is, let's suppose, A. Over here it is A. Area remains same. You guys are supposed to tell me what is the capacitance of this new capacitor. Can you guys tell me in the live chat? Yes, 45 is the correct answer. So we say over here, sir, when we talk about the capacitance of this capacitor, let me just show you the capacitance of this capacitor. You say, sir, that is C is equal to epsilon naught A divided by D. Capacitance of this capacitor. Now, C is how much? You say, sir, 15 is equal to epsilon naught, and then you have A divided by, what is D over here? That is, we say, sir, we say in this case it is 6. Use the same formula over here. Sir, this is also parallel plate capacitor. We can use the same formula. That is, C is equal to epsilon naught A divided by D. Now, what is C over here? We say, sir, this is C dash is equal to epsilon naught area over here is same, divided by, what is the distance between the plates? That is 2. Distance between the plates is 2. Now this is the equation first, this is the equation second. I say divide this with this. So we say over here C dash divided by C dash divided by this 15. Divide, we say C dash divided by this 15. So we say, oh wait, what is the value of C dash? You say, sir, that is epsilon naught A divided by 2 upon, what is the value of this? That is nothing but over here epsilon naught A divided by 6. This and this will get cancelled. So this will be 6 by 2, that is 3. So we say C dash divided by 15 is equal to 3. 15 multiplied by 3, we say C dash is equal to 45 microfarad. I hope this is clear. I hope this is clear. Great, great, great. Yes, which option? Option number 3. Next one, energy stored in a capacitor. Is it clear, guys? Now, we'll find what is the energy stored in a capacitor. We say, sir, capacitor is a device which stores the energy. Now the question is, how much energy does it exactly store? What is the formula for that? How do we have to find that? Okay. Now in this particular case, listen to me very carefully. Let's suppose we have a capacitor, we have a parallel plate capacitor over here. We have a parallel plate capacitor over here. Okay. Now what we are doing is that we'll connect a battery to this parallel plate capacitor. We'll connect a battery to this parallel plate capacitor. Listen to me very carefully. I'll give you the feel of this particular topic. We have a parallel plate capacitor. We'll connect a battery to this parallel plate capacitor. Yes, sir. Now, sir, what does the battery do? What is the work of battery? Listen to me very carefully. See, when I was discussing the electric potential energy, electrostatic potential energy, at that point of time, I was telling you that I am basically bringing a charge from infinity and placing it at some position. I hope you guys remember. I hope you guys remember. So I was doing the external work done over here. Same is the case in this one. Listen to me very carefully. If we have a capacitor, we have a battery over here. So battery will take the charge from one plate. We say, sir, this plate is neutral. The amount of positive charge it has is equal to the negative charge. The amount of positive charge it has is equal to the negative charge. So this battery will take from charge from one plate, it will take the charge and it will place onto the another plate. So battery will basically do the work done over here. Battery does not produce the charge. Battery does not produce the charge. Battery does not supply the charge. Battery basically moves the charge from one plate to another plate. So we say the battery will do the work done in moving the charge from one plate to another. Remember the statement, sir. What does the battery do? If we have a parallel plate capacitor, we connect a battery, it will take the charge from one plate, it will place onto the another plate. If battery takes, let's suppose it will take the small positive charge from one plate and it will place it onto over here. If positive charge comes onto this plate, we say more negative charge will come onto this place. We'd say negative charge will. Same amount of positive, same amount of negative. Don't get confused over here. Or you can understand it something like this also. This battery will take the electrons from this plate and will place it over here on this plate. The negative charge will be occupied here. If negative charge comes onto this plate, we say positive charge will come onto this plate. So if battery will basically get more negative charge from this plate, more positive charge from this plate and will place onto this plate. So on this one, negative charge will be occupied. If more negative charge is placed over here, more negative charge will be occupied over here. This is positive, this is negative, this is positive, this is negative. So we say after some time plus Q charge is placed, after some time minus Q charge will come onto this plate. I hope this is clear. So battery will do one thing, it will do the work done. The battery will do the work done in moving the charge from one plate to another plate. It will take the charge from one plate and it will occupy it onto the another plate. If positive comes over here, negative will come over here. I hope this is clear. I hope this is clear. Yes, sir. Yes, sir. Now, listen to me very carefully. Now, can we say, if charge comes onto the plates, so we say charge has been stored, or we say energy has been stored. So we say the battery will do the work done in moving the charge from one plate to another plate. Now, charge has been stored on the plates, or you say between the plates. Okay, so energy is stored. Energy is stored. Yes, sir, energy is stored. Now listen to me very carefully. Energy is stored in the form of charge. Now listen to me very carefully. We say over here, let's suppose the capacitance of this capacitor is C. Capacitance of this capacitor is C. Now in this particular case, to find that energy, we have to find that energy. See, we say that energy is equal to, listen to me very carefully. We said this U is equal to, what is the charge stored on the capacitor? You say over here it is plus Q minus Q. As a whole, we say it is Q. Q charge has been stored on the capacitor. So we say energy stored in this capacitor will be, in which Q charge is stored, we say Q square divided by. And what is the capacitance of this one? That is C. So multiply with 2. So this is the energy stored. If somebody asks you, Q charge is on the capacitor, how much is the energy stored? You say Q square divided by 2C. Now you just tell me one thing. I'll tell you over here. We say, sir, energy U is equal to Q square by 2C. Okay, great. Sir, we know, sir, as this Q is equal to C into V. We know the formula for Q is equal to C into V. Can we put it over here? Yes, sir. We say U is equal, instead of Q, we write C square, V square divided by 2C. Can we write it something like this? Yes, sir. Now this C and this square will get cancelled out over here. U is equal to, this will be nothing but 1 by 2 CV square. This is also the formula for energy stored in a capacitor, but in terms of C and V. This is in terms of Q and C. So we say this is the energy stored in terms of C and V. In terms of C and V. Now, sir, as we know, C is equal to Q divided by V, because Q is equal to CV, so C is equal to Q divided by V. So can we put it over here? So we say U is equal to 1 by 2. Instead of C, can we put, this is nothing but Q by V? Yes, sir. Because C is equal to Q by V, I'll put it over here, Q by V, and then you have this V square. This V and this square will get cancelled. U is equal to 1 by 2 Q into V. Sir, this is also the expression for the energy stored in a capacitor. Yes, but in terms of Q and V. This is the energy stored in terms of Q and V. I hope this is clear. Guys, let me know. Let me know in the live chat. Is it clear? Is it clear? Is it clear to each and everyone, guys? Yes, great, 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 great. Okay, okay, great. Let's move on to the next one. So, if somebody asks you what is the energy stored in a capacitor, you say, sir, Q square by 2C, 1 by 2 CV square, 1 by 2 Q into V. All the three expressions are correct. A capacitor, okay. Can you tell me the answer of this question? A capacitor of capacitance 700 picofarad, PF, is charged by 100 volt battery. The electrostatic energy stored by the capacitor is, we are supposed to find the energy stored in a capacitor. See, in this particular case, in question, what is given is that is capacitance is given as 700 picofarad, okay? And if you convert this picofarad into farad, then multiply it with 10 raised power minus 12. That's it. And voltage is given, V is equal to 100 volts, okay? The electrostatic energy stored will be, we are having a capacitor which has this much of capacitance and this much of potential. We are supposed to find how much is the energy stored. You tell me one thing, in these three formulas, which formula shall I use? Q square by 2C or 1 by 2 CV square or 1 by 2 Q into V? We can clearly say that, sir, we can use this formula. We have to use this formula. Why? Because capacitance is given, potential is given. So we say U is equal to 1 by 2. See, capacitance is given, potential is given. 1 by 2 C. C is how much? That is 700 into 10 raised power minus 12. Because this is given in the picofarad, we have to convert it into the farad. So that is 700 into 10 raised power minus 12. And then you have multiplied by, this is 100, 1 by 2. We say U is equal to 1 by 2 CV square. Instead of C, I am writing this. Instead of V, V is 100, so it will be V square 100 square. So U is equal to 700 divided by 2 is 350 into 10 raised power minus 12. 100 square is 10 raised power 4. 10 raised power minus 12, 10 raised power plus 4 is 10 raised power minus 8. This is 350 into 10 raised power minus 8. And can I write it something like this? 3.5 into 10 raised power minus 6 joules. 3.5 into 10 raised power minus 6 joules. Great, great, great. B is the correct option. Let's move on to the next one. Yes, yes, yes. See, as of now, you just keep it as it is. Okay, we'll solve these two questions at the end. Because over here, the two capacitor, okay, I'll show you right now only. See, in this particular case, in this particular, we'll have to study this in capacitors in series and capacitors in parallel. But right now, you just remember one thing only. That is, see, we have a capacitor over here. This is the capacitor 1 and this is another capacitor 2. Its capacitance is C, its capacitance is C by 2. Now, the battery connected is having the potential difference V. Yes, sir, it is having the potential V. Now, we are supposed to say in this particular case, the two condensers, one of capacity C, other of capacity C by 2, are connected to a V volt battery. This and this are connected to this battery. The work done in charging the work done by the battery in charging both the condensers is. Now the questioner is saying that when we have connected these two capacitors with the battery, now the battery will send the charge to these two capacitors. Battery will charge these two capacitors. We have to find how much work has been done by the battery in storing the charge over here, in storing the energy over here. I hope you got the question. Now, as I told you, when we were discussing this thing, the battery will do the work done in moving the charge from one plate to another. One more important point you can write over here. That work done, which battery will do, will be stored as, will be stored in the form of energy in capacitor, as will be stored in the form of energy in capacitor. Means, see, battery is doing work in taking the charge from one plate to the another plate. So this work done of the battery will not be lost. It will be stored as the energy of the capacitor. Means, if you have to find the work done by the battery, you find the energy stored in the capacitor. It's one and the same thing. So we say to find work done by the battery. Over here, battery will charge this capacitor, We'll have to find how much work done battery will do. So we say, if we have to find the work done by the battery, we will find energy stored, because that work done will be stored as the energy only in the capacitors. We'll find the energy stored in the capacitor. Yes, I hope you got it. Now, you guys tell me one thing. See. Sir, this capacitor and this capacitor, clearly you can see these two are in parallel. Remember, as of now, for 10 to 15 minutes afterwards, we'll have to study this. If two capacitors are connected in parallel to each other, their equivalent capacitance is, we say, C equivalent is equal to C1 plus C2. In class 10th, you have studied this. If two resistors are connected in series, their equivalent resistance is R1 plus R2. Over here, if two capacitors are connected in parallel, we say their equivalent capacitance is C1 plus C2, net capacitance. So it is C1 is C plus C2 is C by 2. So this will be 2C plus C by 2, that is 3C by 2. So C equivalent is nothing but 3C by 2. So we say, sir, energy stored will be 1 by 2 C equivalent into V square. U is equal to 1 by 2. How much is the net capacitance of this one? Because two capacitors are over here. That is 3C by 2 into, what is V? V is the battery over here, that is given V only, that is V square. So this will be, that is 3C by 4 into V square. So this is the energy stored in the capacitors, and this will be equal to the work done, because work done by the battery will be stored as the energy stored in the capacitor. So we say 3 by 4 CV square. Is this clear? Is this clear to each and everyone? Is this clear to each and everyone, guys? Yes, great. Now, let's move on to the next one. Okay. This was the question which was asked in NEET 2017. Can you guys follow this particular question? A capacitor is charged by a battery. Okay, we have a capacitor. It is charged by a battery. Okay. This capacitor is charged by a battery. Okay. Now, how much will be the energy stored in this one? We say, sir, UI is equal to 1 by 2 CV square. Because energy stored in a capacitor is 1 by 2 CV square. Okay. Now, the battery is then removed. Then we remove this battery. And an identical uncharged capacitor is connected in parallel. If we remove this battery and then an identical uncharged capacitor is connected in parallel. If we remove this battery and then this capacitor, we connect one more capacitor with this, which is identical, similar to this one, but this is uncharged. And you are supposed to say the total electrostatic energy of the resulting system is what is the energy finally? Initially, this much is energy. What is the energy finally if this happens? This is uncharged and this is charged. This is your homework, okay? Or at the end, I will be showing you this question also. This is your homework. Come on, let's move on to the next one. Okay, this one. Force between the two capacitors. Force between the two capacitors. Force between the two capacitors. Listen to me very carefully. Let's suppose we have a plate, we have a parallel plate capacitor over here. We have a parallel plate capacitor over here. Sir, this is a parallel plate capacitor over here. Yes. On this plate, we say positive charge is present. This is positive plate. And on this plate, a negative charge is present. This is negative plate. Okay. Some battery has charged it before. So we say positive charge over here, negative charge over here. Okay. Sir, we know this positive plate will attract this negative plate with some force. Yes, sir. Because positive, negative attracts. Similarly, this negative charge will attract this positive charge towards itself with some force. Yes, sir. So we say, two plates are having opposite charge on each other. Two plates are having opposite charge on each other. Positive, negative. So they will attract and apply force on each other. So they will attract each other and apply force on each other. And we have to find that force, how much that force will be. To find that force, we have to find that force. This is the concept. Force between the parallel plates, force between the plates of a capacitor. Now listen to me very carefully. Let's suppose the charge on this plate is plus Q. The charge on this plate is minus Q. From now onwards, if I say charge on one plate is plus Q, charge on another plate is minus Q, it means charge on a capacitor as a whole is Q. Okay. Now we say that force will be Q square. What is Q? Q is the charge on the capacitor upon 2A. A is what? A is the area of plates. Okay. 2A, and then we have epsilon naught. So this much will be the force. They will apply this much of force on each other. So force between the plates of a capacitor is Q square upon 2A epsilon naught. Now you guys tell me one thing. Sir, in the last one shot, you have told us, sir, sigma is equal to total charge upon total area. Lambda is equal to total charge upon total length. Rho is equal to total charge upon total volume. Now, can you tell me over here, what is sigma? Sigma is the charge per unit area. Now, can you tell me what is the value of Q? Q is equal to sigma into A. Sir, can you put this sigma into A over here? Yes. So we say F is equal to, instead of Q, we can write sigma square. Then we have A square upon 2A. Then we have epsilon naught. This A and this will get cancelled. So what remains over here? We say what remains in this particular case, we say F is equal to, we say sigma square A upon 2 epsilon naught. This is also the expression for force, but in terms of, this is also the expression for force, but in terms of sigma or Q? In terms of sigma. In terms of sigma. And this is the expression. This is the value of force in terms of Q, in terms of charge. Is it clear, guys? In the live chat, I just need to know. Is it clear, guys? And if somebody asks you, how much is the pressure? We say, sir, pressure is nothing but force per unit area. Force upon area is pressure. And how much is the pressure force over here? Sir, force is sigma square A upon 2 epsilon naught. So we can write sigma square A upon 2 epsilon naught. Then we have, this is force upon area multiplied this A. A and A will get cancelled. So pressure will come out to be sigma square upon 2 epsilon. This is the force. This is the pressure. This is the pressure. Great, great, great. Now, so force between the plates of a capacitor is, in terms of charge, F is equal to Q square upon 2 epsilon naught. In terms of sigma, sigma square into A upon 2 epsilon naught. Now, guys, this was the question which was asked in, I hope this is visible. Yes, this was the question which was asked in J Mains 2021. I want you guys to understand this. Let me just tell you what is the question saying. We are given a parallel plate of a capacitor. I'll make you understand the question. We have a parallel plate. This is positively charged. This is positively charged. And this is negatively charged. Okay. Okay, first of all, tell me one thing. If I say, let's suppose I have a positive charge over here. Let's suppose this is a negative charge over here. Can I say, sir, when it comes to the positive charge, electric field is away from the charge? Yes, sir. And when it comes to the negative charge, electric field is towards the charge? Yes, sir. Now, as a whole, between positive charge and negative charge, can I say electric field is from positive charge towards negative charge? From positive charge towards negative charge? Yes, sir, I can say it something like that. Now, in this particular case, can I say, sir, this is positively charged plate, this is negatively charged plate? We say, sir, electric field is from positive charge towards negative charge. This is the electric field. Now, you guys tell me one thing. In this particular question, what is given is that we have got positive plate, we have got negative plate. And an electron enters this region. This is the electron which is entering this region. Okay? It is entering something like this. Now, while electron is entering this region, it is making the angle of alpha. This angle is given as alpha. And it enters with a velocity u. This is the electron. This is the electron. We have positive plate, negative plate. Electron enters this region with velocity u. And this angle is given as alpha. And listen to me very, very carefully. We say, sir, if this is the electric field in the downward direction, I have told you in the last session, if you have, for example, this is the electric field, and inside this electric field, if you place a negative charge, on this negative charge, force will act in the backward direction. Force will act in the backward direction, opposite to the direction of electric field. And if this is a positive charge, we say force acts in the same direction. Force acts along the same direction. Now see, in this particular case, sir, this is the electron. Electron is having negative charge. Sir, this is the electric field's direction. We say force on this electron will be in the upward direction. Now, the path of this one, listen to me very carefully. Listen to me very carefully. We say, sir, the path of this one was supposed to go something like this, but it will deviate from its path. It will deviate from its path and it will leave something like this. It makes an angle of beta over here and leaves with a velocity v. This electron leaves with a velocity v, makes the angle beta over here. Now listen to me very carefully. We are supposed to find the ratio of kinetic energy. It has got kinetic energy K1 over here. It has got kinetic energy K2 over here. We have to find the ratio of this kinetic energy. I'll make you understand this once again. Sir, if an electron enters this region, okay, with a velocity u, and it leaves this region with a velocity v, here it makes angle alpha, here it makes angle beta. We are supposed to find if its kinetic energy over here is K1, if its kinetic energy over here is K2, we have to find the ratio of K1 by K2. We have to find the ratio of K1 by K2. Now, you guys tell me one thing. We have to see according to the options over here. Listen to me very carefully. Sir, when it comes to the kinetic energy, we say kinetic energy is 1 by 2 mv square. So at this particular point of time, what is the kinetic energy? 1 by 2 m, mass of electron, into its velocity. Velocity is u. So we say it will be 1 by 2 m u square divided by, when this electron leaves at that point of time, velocity is v. So we say 1 by 2 m v square. This will get cancelled. K1 divided by K2 is nothing but u square by v square. Now let's check for the options. So no option is matching over here. Now the point is, we have to see according to these options. I hope these are visible. This is sine square of beta, cos square of alpha. Cos square of beta, cos square of alpha. This is cos beta, cos alpha. You guys tell me one thing. Listen to me very carefully. I know this is a bit difficult question, okay? But you have to understand it. You have to understand it. I have included all the pattern questions over here. Now see, this is V. Can I say, sir, V has got this component as, sorry, U, this is U cos of theta. Yes, sir. And this is V. This will be its, this is V. This will be its V cos of beta. Yes, sir. This is alpha. This is alpha. Let me call this as alpha. If this is U, this is alpha. So this will be U cos alpha. If this is V, this is beta, and this will be V cos beta. And in this particular case, we say, sir, this U cos alpha, U cos of alpha will be equal to V cos of beta. V cos of beta. Why, sir? Because in x direction there is no force. So this velocity will remain same. It's, remember directly, horizontal velocity will remain same over here. That's why U cos alpha is equal to V cos beta. Now we say, sir, U cos of alpha is equal to V cos of beta. Now we say U divided by V is equal to cos of beta divided by cos of alpha over here. Now instead of U by V, can I just put up over here, sir, K1 divided by K2 will be, instead of U by V, we say, sir, cos square of beta divided by cos square of alpha. That's what I was trying to explain. So this is the option B. See, the question was, we have an electron, it enters this positive, negative, this region in which electric field is present. And it enters with a velocity u, makes angle alpha. When it leaves, it has velocity v, makes angle beta. So we are supposed to find, if it has kinetic energy over here K1, over here it has K2, we have to find K1 by K2. Some people can avoid this question, some people can take this question, but I just need to know how many of you guys understood this in the live chat. Then I can move forward. Can you solve this question? Let me know. Can you tell me what is the answer of this question in the live chat? Can you tell me the answer of this question? We don't have to deal with the vertical velocity over here, because we got the answer by taking the horizontal velocities only. That's why I didn't mention anything about the vertical velocity. Is it clear, guys? Okay, great. Now see, we have got, find the force of attraction between the plates in terms of C, V and D. We have got the plates over here. We have got a parallel plate capacitor, and the capacitance is C Potential difference is V, and distance between the plates, separation, is D. You guys are supposed to tell me. You guys are supposed to tell me the force between the plates, but in terms of C, V, and D. Sir, we know force between the plates is Q square upon 2A epsilon naught. Sir, is this correct? We say no. We have to find the force, that formula of force in which P is present, V is present, and D is present. Over here, Q is present and A is present. So we don't need this formula. Now, sir, we know as Q is equal to C into V. Yes, sir. Now, instead of Q, we'll put CV. So we say F is equal to, instead of Q, we say C square into V square upon. And we say over here, this is 2A, then we have epsilon naught. Sir, can we just write it something like this? Take one C out. We say, sir, this is C. And then we have V square upon. Then we have, this is 2A. Then we have epsilon naught. And then we write this C in the separately over here. Yes. Now, sir, we know the capacitance of a parallel plate capacitor. That is epsilon naught A by D. This is a parallel plate capacitor. Its capacitance is epsilon naught A divided by D. So instead of this C, what we will be doing is that C V square upon 2A epsilon naught. And instead of this C, what we'll do is that epsilon naught A divided by D. Now this epsilon naught A and this epsilon naught A will get cancelled out. So what remains? We say, sir, C V square divided by 2D. So what is the final expression? Final expression for force, final expression for force is nothing but CV square by 2D. So we got the force in terms of C. C over here, V, and then D. So this is the answer of this particular question, CV square by 2D. Yes, great. Next. Can you tell me the answer of this was asked in NEET 2018. The electrostatic force between the metal plates of an isolated parallel plate capacitor having a charge Q and area A is. The electrostatic force between the plates of a metal plates. We are supposed to tell the force between the plates of a capacitor is independent of the distance of the plates. We say, sir, yes. Linearly proportional to the distance between the plates? No. Sir, when it comes to the force, we say it is Q square upon 2A epsilon naught. Force between the plates of a capacitor, that is Q square upon 2A epsilon naught. And in terms of sigma, if I just write, it is how much? See, Q is equal to, we say sigma square A square upon 2A epsilon naught. This and this. So it will be sigma square A 2 epsilon naught. See, in terms of sigma, there is no distance. Over here, there is no distance. Distance means there is no separation. No separation term is mentioned in the force over here. So we say the electrostatic force between the plates of a capacitor is independent of the distance between the plates. Sir, do not say over here it is saying it is dependent. No, we have just converted. It is the question in which it is saying that you have to convert it in terms of CV and D. But when we look at the general expression, in the general expression, there is no D term. I hope this is clear. Then we have the term battery. Is it clear? Is it clear to each and everyone, guys? Show me the fire symbols in the live chat. Is it clear, guys? Let me know with the fire symbols in the live chat. Is it clear to each and everyone? Great. Now we have the battery over here. We have the battery over here. Listen to me very carefully. Listen to me very carefully. See, when it comes to the battery, sir, we know the symbol of capacitor is these parallel plates. These two parallel plates, it represents what? It represents the capacitor. Sir, when it comes to the resistor, we represent resistor with something like this. Yes, sir. This concept will help us to solve the questions from electricity also, from current electricity. So remember this from now onwards. Sir, when it comes to the battery, we say battery is something like this. This is the symbol of battery. This is the symbol of battery. Yes. Now, what does this means? This means positive terminal and this means negative terminal. Or you can call this as higher potential and this is what we call lower potential. And this is the symbol of battery, This is higher potential, lower potential. Or you can say this is positive terminal and this is negative terminal. Okay, cool. This is the appropriate term. Higher potential, lower potential. Cool. Now in some of your questions or in books you might have seen, sir, it is mentioned, we have seen many times it is mentioned over here 20 volts or it is mentioned over here 30 volts. What does this 30 volt, what does this 20 volt actually mean? What does it signify? Listen to me very carefully. We say this is nothing but this means delta V, which means potential difference. Potential difference. This is potential difference. Or we say this is nothing but EMF. Remember it directly. This means potential difference slash it means EMF. As simple as that. Now, let's suppose if I tell you, sir, we have a battery over here. This battery has 20 volts. What is this 20 volt? This is potential difference or this is EMF. So over here, we always mention EMF or potential difference. But when it comes to this point, this is a point. So we say this point has potential difference. This point has potential. It has potential. Sir, what is that? If I say, let's suppose, for example, this is plus 20 volts over here. What does that mean? That means potential at a point. This point has a potential, but this battery over here, it has potential difference. Always remember, let's suppose, I'll give you one more example. This is 30 mentioned over here. And this is at this particular point, it is mentioned, we say also 30. Let's suppose this 30. What does this 30 mean? This is nothing but potential at a point. This is nothing but potential at a point. And what does this 30 volt mean? This is nothing but potential difference. I hope you got it. And remember from now onwards, always, let's suppose we have this battery. The name of the point is A. And let's suppose this is B. This is A and this is B. We say this is over here delta V. Always remember, sir, this potential difference, we say this delta V is nothing but always VA minus VB. What does potential difference mean? It means higher potential minus lower potential. So this is positive terminal is at higher end. So we say that is higher potential is plus A. So we say this lower potential is B. That's why VA minus VB. If I say, let's suppose in this particular case, let me show you some of the questions. Okay. Can you tell me what is the value of potential difference in this case? If I say, let's suppose this is 6 volts and this is 3 volts. Sir, what is this? This is potential of a point. This is potential at a point. This is delta V. So we say delta V is nothing but VA minus VB. Sir, let's suppose this is VA and let's suppose this is VB. So we say delta V is nothing but, what is the value of VA? That is 6. Minus, what is the value of VB? That is 3. 6 minus 3 is 3 volts. Means this is nothing but 3 volts. Yes, great. Can you tell me what is the value of potential difference over here also? Sir, delta V in this case is also, this is A, this is B. VA minus VB. That is 3 minus 0. That is 3 minus 0 is 3. Can you tell me what is the value of potential difference over here also? Sir, over here also potential difference is VA minus VB. Always take this as higher potential. Means this is potential at A, this is potential at B. What is potential at A? That is 0. We say, sir, this is 0. Minus, then you have, just a second. Then you have this minus, formula minus, okay. VB, what is the value of VB? That is minus 3 volts. So we say 0 minus into minus becomes plus. So this is plus 3 volts. So over here also potential difference is 3 volts. Great, great, great. Now, can you solve these questions? Can you tell me the value over here? What is the value of VB? VA is given as 0. Delta V is given as 10. What is the value of VB? What is the value of VB? Everyone, everyone. See, in this particular case, sir, we always say VA minus VB is equal to, we say delta V. Okay. VA minus VB in this case is basically delta V. Now, tell me, see, I have put up this higher terminal from this side. Change in potential, change in potential. How you can write this? How you can write this in this particular case? Tell me. See, this is positive terminal is from this side. Positive terminal is from this side. Can you guys tell me in this particular case? In this particular case. Okay, all the people out there. Sir, we can clearly say in this particular case, that is nothing but we say higher minus lower. Okay, so we say this is nothing but in this particular case, this is VB minus we say in this particular case, that is over here VA is nothing but we say, sir, 10 in this particular case. Okay, so now in this particular case, this is VB is equal to, that will come out to be 10, as simple as that. Okay. You say over here, what is the value of this one? Can you guys tell me? Can you guys tell me in this particular case? This one. See, take this as higher. Take this as higher. This is lower. Now, in this particular case, you will take this as higher. Okay. So you say over here, sir, this will be VA. Higher minus lower. Consider this as VB. So this is VA minus VB. VA minus VB is equal to, sir, delta V. Now, what is VA in this particular case? Sir, we are supposed to find VA in this particular case. Okay. And then you have minus. What is the value of VB? VB, value of VB in this particular case. Okay. We are supposed to find VA. VB is, that is nothing but we say minus 10 over here is equal to, we say, sir, 20. Sir, minus into minus becomes plus. VA plus 10 is equal to 20, and VA is nothing but 20 minus 10 is 10 volts. Great, great. It is 10. See, this is VA minus VB. VA minus VB is equal to delta V. VA write as it is. VB is nothing but minus 10. So I'll write minus 10. This minus is the formula's minus, and delta V is given as 20. So 20. Solve it, you will get this one. Now you will do this and this by yourself. Okay, great. Let me just show you. I had to teach you this particular concept. That's why I was teaching you the previous one. Now see, let's suppose we have over here a capacitor. Its name is C1. Okay. And then let's suppose we have another capacitor. its name is C2. Okay, the capacitance of this capacitor is C1, the capacitance of this capacitor is C2, and one end of capacitor is over here. Let's suppose the potential of this is V1. You call it VA, you call it V1, whatever it is. And
Just a second, guys.
okay, great. Now see, so we say this end, the another end, the end of this capacitor C2, it has got potential V2. This end has V1, this end has V2. Now, can you see over here, sir? This capacitor has another end over here. This capacitor has this another end over here also. So means this end, which is in between, is common to this capacitor as well as this capacitor. So we say this is common to both. This is common to both. This, listen to me once again. This end has potential V2. This end has potential V1. And this is the end which is common to this one as well as this one. So the potential of this end is what we call the common potential. The potential of this end is what we call the common potential, because this end is common to both the capacitors. And if the questioner asks you, what is the value of this common potential? Or you say this is midpoint potential. So we say this midpoint potential is equal to this. Remember it directly. We say, sir, it is nothing but P1, this capacitor, its capacitance, into, we say V1. Then plus this capacitance C2 into its potential, that is V2. Upon, we say its capacitance C1 plus its capacitance C2. C1 V1 plus C2 V2 upon C1 plus C2. This is the most important formula that will help you to solve bigger problems. I'll be showing you. Sir, let's suppose we have got a question something like this. Can you solve this particular question by using the same common potential method? Sir, we know, sir, we have to find the value of this one, V. Are you able to see this question? Yes, we are supposed to find the value of this V. See, in this particular case, we have got three capacitors. This one, and this 6 microfarad. This one end of this is having the potential. Just a second. This end has got the potential of 20 volts. 6 microfarad has this end, it has got 20 volts. This end has got potential of 50 volts, minus 50. This end has got the potential of 10 volts. You guys are supposed to tell me this end, which is in between, which is a common end to all the three capacitors, you have to find its potential. Sir, the formula is, see, this one, even you can see, sir, you can make it something like this. If we have the capacitor, if we have another capacitor, let's call this as C1, let's call this as C2, let's call this as V1, let's call this as V2, let's call this as V3, and let's call this as C3. Don't you think this end, which is in between all the three, this is common end, so this VC is equal to, remember it, C1 V1 plus this C2 V2 plus this C3 V3 upon, we say C1 plus C2 plus C3. This is how do you find the common potential. We'll use the same approach over here. So we say, sir, VC is nothing but this common potential. C1 V1, what is C1? Take this capacitor as C1. V1, its potential as V1. So we say C1 V1 plus C2, this capacitor V2, C2 V2 plus C3 V3 upon, we say C1 plus C2 plus C3. So we say VC is equal. What is C1? C1 is 2. 2. And what is V1? That is, sir, 10. Plus, what is C2? That is 4 into, what is V2? V2 is minus 50. Take it minus 50. So this is minus 50. Plus, what is C3? That is 20. And, sorry, C3 is 6. C3 is 6. And what is this? V3? That is 20. Okay. Upon C1 plus C2 plus C3. C1 is 2. C1, C2 and C3. That is 2 plus 4 plus 6. If you solve it, it will come out to be minus 5 volts. Yes, minus 5 I can see in the comments, in the live chat. Great. Great, great, great. Great. Yes. Now, okay. Another type of question. I want you guys to solve this type of question also. Listen to me very carefully. We have got a circuit. This is a circuit. Okay. And over here, we have got 10 volt battery. This is 20 volt battery. This is another 10 volt battery. And this is a capacitor. See, whenever you have two lines, parallel lines, it means capacitor. Whenever you have one line which is longer and another which is shorter, means it is a battery. So 2 capacitors and 3 batteries. First and the foremost thing is you are supposed to find the potential of this point. Okay. Second, you are supposed to tell me how much charge is stored in this first capacitor, Q1. Find Q1. Second, you guys are supposed to tell me how much is the charge stored in the second capacitor, that is Q2. Now listen to me very carefully. How do I exactly solve this particular question? Listen to me very carefully. See. Sir, when it comes to this potential, remember the trick. Remember the trick. Sir, what is the trick? Assume zero potential. Assume zero potential at a point. At any point. Sir, at what point? See, I'll assume zero potential at this particular point. Why, sir? It will not create any difference, okay? So I am saying you just follow it. Every question will be solved by this technique. So we say, sir, zero potential I am assuming at this point. Will it create any sort of difference over here? No. Zero potential is exactly at this point. Now listen to me very carefully, my dear friends. If I am assuming zero potential over here, listen to me very carefully. I'll take this battery over here. This battery over here. This is 20 volts. What is the first thing that you'll do? You'll assume the zero potential. So I'll assume the zero potential at this point. So I'll take this 20 volt battery. This is the 20 volt battery. So at this side, on this side, what is the potential? You say, sir, 0 volts. Now, can you guys tell me, sir, if this potential difference is 20 volts, this end is having the 0 volts, what is the value of potential at this end? Sir, let's suppose this is VA, this is VB. We know VA minus VB, that is 0, is equal to delta V, that is 20. Yes, sir. So VA minus 0 is VA. So VA will come out to be 20. Means this point, this end has got the potential of plus 20. We say this end has a potential of 20 plus 20 volts. I hope you got it. VA minus VB. That's why I showed you the previous, those questions. Yes. Great. Now, similarly, if you take this battery right now, sir, this is the battery over here. This is 10 volts and this is the 0 volt battery. This is the 0 volts. Now you guys tell me one thing in this particular case. If this is 0, this is 10, what is the value of this one? Remember, sir, we say the value of this one will be how much? Will this be plus 10 or minus 10? This will be, sir, minus 10. Why? I'll tell you. See, this is this 0. This should be at higher potential. This is at higher potential. And this is at lower potential. Let's suppose this is VA. And let's suppose this is VB. VA minus VB has to be equal to, sir, delta V. VA, what is the value of VA, sir? 0 minus VB. We don't know how much is VB. We have to calculate it. VB is equal to this delta V. That is how much, sir? 10. Take this over here. Sir, VB will come out to be minus 10 volts. That's why I was saying this is minus 10. Great. Lot of people are actually able to answer in the live chat. Now see, so we say, sir, if this is having 0 potential from this side, so this end has the potential of, we say, minus 10 volts. Now, if this point has the potential of plus 20, sir, how much is the potential over here? This is also plus 20. Remember, if for example you have got this line, this wire, over here you have got capacitor over here. If this point has got plus 20 volts of potential, over here it is also 20. Over here it is also 20. Why? Because it is simple wire only. But when you see any capacitor, resistor, or anything, any load, so over here it cannot be plus 20, it can be something else. But along this line till here, it will be plus 20 only. So from this point to this point, it is a simple wire, that's why plus 20. So at this point also it will be minus 10 volt. Is it clear, guys, or I am confusing you? Is it clear to each and everyone, or I am confusing you? These are the important questions. Is it clear? Okay, similarly, you have got this 0 volt over here. If this is 0, how much this will be? This will be plus 10 volts. As simple as that. So first, we got the value of this one. Great. We got the value of V is equal to, we say, plus 10 volts. Now, we have to find the charge in this. We have to find the charge in it. It is simple. To find, if we have to find Q1. Sir, we know if we are supposed to find charge in a capacitor, we say Q is equal to C into V. It is not V, it is actually delta V. We can write it V, it is one and the same thing. V delta V, it is one and the same thing. So Q is equal to C delta V. C is the capacitance, delta V is the potential difference. Now, charge in this capacitor Q1 is equal to, capacitance of this capacitor is how much? You say, sir, 4, because 4 is given. Delta V, potential difference. That is final potential minus initial. Higher potential minus lower. Sir, from this side it is plus 20. From this side it is 10. So we say delta V is V2 minus V1. Or you say VA minus VB. Sir, how much is this? This is 20. So we say 20 minus. From this side, how much is potential? That is 10. See, I'll make it over here. This is the capacitor. This is 4 microfarad. From this side, it is 20 volts. From this side, it is 10 volts. So Q is equal to C into V into delta V. Delta V is how much? This potential minus this potential, 20 minus 10. 20 minus 10 is 10. So that is 40 microcoulomb, Q1. Similarly, you can find the value of Q2. Q2 is nothing but C delta V. So what is the value of C? Value of C, charge in the second capacitor, that is 2. So we say this is nothing but 2. And what is the value of delta V in this case? Sir, delta V is how much? See, it is plus 10 minus 20. Higher minus lower. 10 minus of minus 10. So we say it is 10. So we say it is 10 minus of minus 10. Okay. So we say this is 2 into minus into minus becomes plus. This is 20. So this will be 40. Great. Yes, yes. Is it clear? Now, can you solve this question, guys? Can you solve this question? You are supposed to tell me the charge in this one, Q1, charge in this Q2, and the potential of this point. And the potential of this point. Hey guys, remember, over here, this is not a battery, this is a capacitor. Previously, it was a battery over here. But now I have kept the capacitor over here. You guys are supposed to tell me the potential of this point first, that is the midpoint potential, and then charge in this capacitor, charge in this capacitor. Can you guys tell me the answer of this one? See, how do I solve this? How do I solve this? Listen to me very carefully. Listen to me very carefully. Sir, first and the foremost thing is we'll find this potential, common potential. Let's find common potential VA. Let's find, we say VA. First and the foremost thing is we'll find the common potential. Let's suppose VA. Okay. Let me make it over here. What is the first thing that we do? We assume zero potential at a point, sir. So let's suppose I am assuming the 0 volt potential at this point. If it is 0 volt over here, guys, tell me how much is the potential at this particular point? I have showed you previously. So this is nothing but that will be plus 20 volts. If this is 0 and this is over here a 10, how much this will be? This will be plus 10 volts. See how? 20 minus 0 will be 20. VA minus VB has to be equal to delta V. VA is 20 minus 0 is 20. 10 minus 0 is 10. If this is having 10, this is having plus 20 over here also. This is 10. This is having plus 10 over here also. Now guys, take these 3 capacitors. I'll redraw it. Redraw this circuit. I'll show you how to solve it. So first and the foremost thing is I'll make this capacitor. Then I'll make this second capacitor. Then I'll make this third capacitor over here. So this is how much? That is 5 microfarad. What is the value of this? This is 4 microfarad. What is the value of this? Is 1 microfarad. Okay. And the potential of this end, that is plus 20 volts. Potential of this end, that is plus 10 volts. And the potential of this end is 0 volts over here. Yes. Now, how can we solve this? We are supposed to find this potential. Don't you think, sir, this is a midpoint potential? Yes, we know the formula. Sir, midpoint potential formula is how much? VC is equal to V1 C1. C1 V1. C1 is 5. V1 is how much? That is 20. Plus C2 V2. C2 is 4 and V2 is, sir, 10. Plus C3. C3 is 1 and V3 is 0. Upon. We say C1, 5 plus 4 plus 1. C1 plus C2 plus C3. And if you solve this, 100 plus 40, 140 divided by 10. So this will come out to be 14 volts. Is it 14? Yes, it is 14. It is 14. Now, similarly, you can find the value of Q1 over here. Q1 is equal to C delta V. Similarly, Q2 is equal to C delta V. Done. Sir, Q1 is equal to capacitance of this capacitor, that is 5. Delta V, see, this is 14 volts, means this will be 14 volts. This is 20, this is 14. So delta V is 20 minus 14. So we'll say, sir, 20 minus 14. So Q1 is equal to, that is 6, that is 30 microcoulomb. Similarly, you can find the value of Q2 also. Is it clear, guys? Great, great, great. Yes, yes, yes. Similarly, what is the value of Q2? Can you guys tell me what is the value of Q2? This one. That is C is equal to Q delta V. Q is 4. Delta V is how much? 14 minus 10. We always do higher minus lower. VA minus VB means higher minus lower. Over here it is higher is 14 minus 10. Don't say 10 minus 14. Here also this is 20 minus 14. Okay, higher minus lower. Great, it is 16. Yes, yes. 14 minus 10. We say 14 minus 10 is 4. 4 into 4 is 16. Yes, Q2 is 16. Great. Microcoulomb. Great, great, great. Everybody is able to answer in the comments. Absolutely cool. Okay. Let's move on to the next one. Okay, we have this topic we have over here. That is, we say, series combination of capacitors. As in your previous classes, you might have studied, we have got resistors connected in series, R1, R2, R3. Now, in this particular case, we have the capacitors connected in series. Okay, we have here 3 capacitors are connected in series. So we have 3 capacitors connected in series. So to find its C equivalent. See, previously, what were you doing in class 10th, class 11, sir? R equivalent, R1 plus R2 plus R3, same is the case over here, what we are supposed to do. Instead of 3, we have to find the net capacitance. To find the net capacitance. Net capacitance. See, we have got C1, C2 and C3. These are the 3 capacitors connected in series. And a battery of voltage V is connected to them. Let's suppose this battery gives a potential difference of V1 to this capacitor. It gives potential V2 to this capacitor. It gives potential to V3. What is this? Potential difference across this, potential difference across this, potential difference across this. Capacitance of this is C1, C2, C3. Let's suppose charge stored in the first capacitor is Q1. Charge stored in the second capacitor is Q2. Charge stored in the third capacitor is Q3. I hope this is crystal and clear to each and every one. Yes, sir. Now, you guys tell me one thing. See, I'll tell you. In series combination, remember, in series combination, we say charge in each capacitor remains same. Charge in each capacitor remains same. Sir, in series combination, charge in each capacitor is same. That means charge in first capacitor will be equal to charge in second, will be equal to charge in third, will be equal to charge. Only we have 3 capacitors over here. Q1 is equal to Q2 is equal to Q3, and let's suppose it is Q. Okay, like in case of resistors, we say current in this is equal to current in this is equal to current in this. Okay, similarly, this charge stored over here is equal to here is equal to here. But we say potential difference will be different. Potential difference in this case is V1, V2, V3. And we say over here, sir, net potential difference, this battery, let's suppose if this battery is having 100 volt, it will give 25 to this, 25 to this, 50 to this. So total is 100. So we say V net is equal to V1 plus potential difference given to first one, then it given to second one, we say V2 plus then given to third one V3. Now you tell me one thing. This is equation number first, this is equation number second. As we know, sir, Q is equal to C into V. Yes, sir, we know this. Can I say from over here, V is equal to Q by C? Yes, sir. I can write V as Q by C. Now, put the value of, instead of this V, can I write Q by C? Yes, sir. I'll write it over here. I'll write it over here. I'll write it over here. Instead of this V net, I'll write C equivalent or C net by V is equal to Q by C net. You say, sir, this is Q by C equivalent or C net is equal to V1. Instead of V1, can I write, sir, this is V1. Instead of V1, I can write Q1 by C1, charge in first upon capacitance of first, Q1 by C1. So I can write Q1 by C1 plus Q2 by C2 plus we have Q3 by C3. Now, equation first says Q1 is equal to Q3, Q2 is equal to Q3 is equal to Q. So all of these are same. So we say, sir, Q by C equivalent is equal to Q by C1 plus Q by C2 plus Q by C3. All these will cancel. So what remains? 1 upon C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C. Means if you have got 3 capacitors in series and you have to find their net capacitance. So what will you do? Sir, you will say 1 upon C net is equal to 1 by C1 plus 1 by C2 plus 1 by C3. This is how you find the equivalent capacitance. Now, guys, can I say, sir, for 2 capacitors in series, if you have got 2 capacitors in series, let's suppose this one and this one, C1 and C2. Can you find their C equivalent? You say, sir, 1 upon C equivalent will be 1 by C1 plus 1 by C2. Then cross multiply it. So 1 upon C equivalent, we can say, sir, this will be C1, C2. C1 plus C2 upon, we say C1 into C2. C1, C2. Now, do the reciprocal. So what you can write over here, C equivalent is equal to C1, C2 upon C1 plus C. Just the basic things, okay? Yes. Is it clear? Is it clear, guys? Okay, cool. This is important. From competition perspective, this is important. Law of potential drop in series combination. What does law of potential drop in series combination mean? Listen to me very carefully. Let's suppose we have got 3 capacitors, C1, C2, C3. Okay. And we have connected a battery to it. And this battery will basically give potential difference V1 to first capacitor, V2 to second capacitor, and V3 to third capacitor. Okay. Yes. Now we know, sir, as we say Q is equal to C into V. Listen to me very carefully. Sir, this is a series combination of 3 capacitors. Sir, general formula we know Q is equal to C into V. Yes, sir. Now over here, can I just write, sir, V is equal to Q divided by C. Yes, sir. I'll take this C over here in the denominator. Yes. Now you guys tell me one thing. Previously, I have told you, in case of series combination, what remains same in all the capacitors, charge or potential difference? We say, sir, charge remains same in each capacitor, but in series combination. So can we say, sir, Q is same in all the capacitors. Q is same in all the capacitors. In all the capacitors, charge remains same. In all the capacitor, charge remains same. Yes, sir. If in all the capacitors charge remains same, means charge becomes constant. So can I say can I say in that case V is inversely proportional to C? Yes, sir. V is inversely proportional to C. So we say V is inversely proportional to C because this is this one. Yes, sir. So means remember this, sir. If this is constant, means potential difference is inversely proportional to the capacitance. Means what does it say? In series combination, listen to me very carefully for just 1 second. Means in series combination, the one which has more capacitance will have less potential difference. Sir, what does it mean? Because V is inversely proportional to C. If, for example, you have got 3 capacitors in series, and if I say the capacitor which is having large capacitance, will it have less potential difference or more? It has less. Why? Because V is inversely proportional to C. V is inversely proportional to C. Let me give you the question over here. Let me give you the question. This is the question on your screen. See, we have got 5 microfarad, 10, I'll make it over here. We have one capacitor, another capacitor, 3 capacitors. And this is the battery over here. We say this is 100 volt. All the 3 capacitors are in series. This is 5 microfarad. This is 10 microfarad. And this is how much? This is 30 microfarad. Can you guys tell me which one will be having more potential difference in all the 3 in the live chat? Which one will be having more potential difference? 5, 10 or 30? 5, 10 or 30? According to the law of potential drop. Which one will be having more potential difference? Yes, 5, exactly. We say, sir, according to law of potential drop, V is inversely proportional to C. But this law of potential drop is valid in case of series combination only. You cannot apply this in somewhere else. So this is valid for series combination only. So we say V is inversely proportional to C. V is inversely proportional to C. Listen to me very carefully. The one which has more capacitance have less potential drop. See, 5, 10, 30. 30 is large. So means potential difference will be less. Now my question to you is, sir, in this particular case, find potential drop across each. Find how much is the potential drop in this, in this. So in each capacitor, how much is the potential drop? Can you guys tell me? I'll tell you the trick. How do you remember? How do you remember this trick? See, sir, we know the one which has more capacitance has less potential difference. So 30 will have less potential difference. We know it. So let's suppose X is the potential difference across 30. X. Now, how much will be the potential difference across 10? You say, sir, this is 30. This is 10. Means 30 is 3 times greater than 10. Because 10, 3 into 10 is how much? 30. So we say, sir, in this case, sir, 30 is 3 times greater. So means over here, the potential difference will be 3x. Or we say, sir, in this particular case, if we talk about this is how 30 is how many times greater than 5? 5, 6 that 30, 6 times. So we say 6x will be the potential difference over here. Potential difference in 30, let's call it x. And this is how many times greater? This is how many times smaller than 30? 3 times. So it will be 3x. So this is how many times smaller than 30? 6 times. So it will be 6x. So we say, this is the trick that we'll remember. This is the trick. Assume this as x. So this will be 3x. This will be 6x. Now if I say over here in this particular case, sir, this is potential difference across this. And in case of series combination, we know this potential difference plus this potential difference plus this potential difference is equal to V net. I have told you over here. V net is equal to V1 plus V2 plus V3. Same is the case over here. Same is the case over here. Sir, this potential difference, that is 6x, plus this potential difference, that is 3x, plus this potential difference x, has to be equal to net potential difference, that is 100. Because battery is supplying only, na? Now in this particular case, 6 plus 3 is 9, 9 plus 1 is 10. So this is 10x is equal to 100. So x will be equal to 10 volts. Means, sir, potential difference across 30 is 10 volts. Now, if x is 10, let's call this as V1. Let's call this as V2. Let's call this as V3. So we say, sir, V3 is equal to x is equal to 10. Can you guys tell me what is the value of V2? You say, sir, the value of V2, potential difference across is, that is 3 into x. X is 10. 3 into 10 is 30. And what is the value of V1? That is 6 into 10. That is 60. See, 60 plus 30 is 90. 90 plus 10 is 100. So this is the 100. Great. Yes, yes. Shall I repeat this question? Do you guys want me to repeat this question? Yes or no in the chats? Yes or no in the chats? Great. Can you solve this question? Can you solve this question? Can you solve this question? See, it is a similar type of question over here also. We have got 3 capacitors. 3 microfarad, 6 microfarad, 18 microfarad and 10 volt battery. Now in this particular case, you are supposed to tell me the potential difference across each capacitor. You guys are supposed to tell me potential difference across each capacitor. You guys are supposed to tell me potential difference across each. See, we have 3. This is the first one, this is second one, and this is the third one. It is very simple now. Sir, this is 3, this is 6, this is 18, and this is 10. Now you guys tell me one thing. See, guys, we know, sir, law of potential drop says potential difference is inversely proportional to the capacitance. In case of series combination only. This is an important statement. Don't mention the parallel combination. In case of series, V is inversely proportional to C. Means the one which has more capacitance will have less potential difference. That is the inverse relation. Yes. So 18 will have less potential difference. Then 6 will have greater than 18. 3 microfarad will have greater than 6 also. Let's suppose potential difference across this 18 is X. Let's call it X. How much will be across 6? You say, sir, this is X. And 6 is 3 times, we say, or 18 is 3 times greater than 6. Because 6 3s are 18. So this is X. So we say this is 3X. Or 6 is 3 times less than 18. Now, this 3 is how many times less than 18? 6 times. 3 6s are 18. So this will be 6x. So potential difference across this is x, 3x, 6x. The more you solve the questions on this, the more you will understand and you will be able to solve each and every question. It needs practice. That's it. So we say, sir, in this particular case, we know V1 plus V2 plus V3 is equal to, sir, V net. What is the value of V1? That is 6x plus 3x plus x. And what is the value of V net? That is, sir, 10 volts. So we say this is 10x is equal to 10. X is equal to 1 volt. So if x is equal to 1 volt, sir, means if this is 1, can you tell me what is the value of 3x? Sir, 3x is equal to 3 into 1 is equal to 3 volts. So this will be 3 volts and the 6x is equal to 6 volts. So across this will be 6 volts. Is it great? Yes, 631. A lot of people have already answered this. Great, great, great. Now we have the we have the parallel combination, okay? Let's understand this parallel combination. See, I'll make it something like this. We have a capacitor over here. We have one more capacitor. This is the capacitor. Let's call this as C1, this is C2, and this is C3. And we'll connect a battery to it. Let's suppose this is the battery V. This is the this is the capacitor. Okay. This is the capacitor. These are the three capacitors connected in parallel. Here capacitors are connected in parallel. Here three capacitors are connected in parallel. Okay. Yes. Now listen to me very carefully. In case of parallel combination, let's suppose this battery is directly connected to C2. This battery is directly connected to C1C. The end of this battery is directly connected to C1. No load is in between. The another end of this battery is directly connected to C2, C1, C3, all the three capacitors. Over here also. So we say in case of parallel combination, potential difference is same. Here capacitors connected in parallel. So we say potential difference remains same across all. But when it comes to the series combination, what was same? We say charge was same across all capacitors. But over here, we say what is same across all? We say potential difference. So across this, it is V, it is V, it is V. So battery will send the same potential difference to all. Now, sir, charge is different. Charge is different. Now how? Let me show you. Let's suppose battery is sending the charge Q over here. This Q gets divided. Some part of the charge will basically go into the capacitor C1. Let's call that Q1. Some of the part of capacitor charge, it will go in the capacitor C2. Let's call it Q2. And this will be, let's call this as Q3. So Q is divided into Q1, Q2 and Q3. This will get stored over here. This Q2 will get stored in the C2. This Q3 will get stored in the C3. So we can write the two equations. I can say over here that is nothing but, sir, V1 potential difference across first is equal to potential difference across second is equal to third. Let it be V. And Q1 charge in first capacitor plus charge in second capacitor plus charge in third capacitor will be equal to the net charge. That is Q. Q is equal to Q1 plus Q2 plus Q3. So I can say it's something like this. Now you guys tell me one thing. As we know, see, we know, sir, Q is equal to C into V. Now, instead of this Q1, can I just write this is C1 into V1? Yes, sir. So we can say over here, this will be C1 into V1 plus, instead of this Q2, can I just write C2 into V2? Yes. Plus, we can say, sir, Q3 will be C3 capacitance of third into V3 is equal. This will be, sir, C equivalent or C net into, sir, V. Okay. We know V1 is equal to V2 is equal to V3 is equal to V. So V1, V2, V3, V all will get cancelled because they are same. So we say C1 plus we say C2 plus we say C3 is equal to C. Okay. So in case of series combination, if you have, listen to me very carefully, In case of series combination, if you have the capacitors connected in series and you have to find the net capacitance, this is how do you find. This is just in case of resistors, what you were doing is that in series combination R1 plus R2 plus R3. Over here it is just the opposite. Now, listen to me very carefully. Over here, we have law of charge distribution in parallel combination. And when it comes to the series combination, in series combination, I have showed you law of potential drop in series combination. But over here, we have what? Law of charge distribution. Let me tell you what is this law of charge distribution. See, let's suppose we have a capacitor over here. We have one more capacitor over here. We have one more capacitor over here. They all are connected in parallel, okay? They all are connected in, we say, parallel. Now, in this particular case, we say this is C1, this is C2, we say this is C3. And we know, sir, over here, the potential difference across first is equal to the potential difference across second is equal to the potential difference across third. Potential difference will remain same across the three. As we know, sir, Q is equal to C into V. Yes. Now, in case of series combination, we say what remains same? Sir, potential difference. V is equal to same. V is constant. If V is constant, means this is constant. So can I say? So we can say Q is directly proportional to C. Yes, sir. What does that mean? The one which has more capacitance will store more charge. So the one which has more capacitance will store more charge, because Q is directly proportional to C. Where? In parallel combination. In parallel combination. This is what we call the law of charge distribution. Is it clear? Now, on the same concept, if I am giving you the question over here, we have got the three capacitors, 3 microfarad, 9 microfarad, 18 microfarad. If I ask you the simple question, which capacitor will store more charge by applying the law of current distribution? 3, 9 microfarad or 18? Let me know in the comments. Let me know in the chat. Let me know in the live chat. Let me know in the live chat. Everyone. Let me know in the live chat. Let me know in the live chat. Yes. Great. 18 will store more charge. Why? Because we know, sir, according to law of, and tell me how much is the charge stored over here. Find it. According to law of potential drop. Law of current distribution. And guys, if you have not liked the session yet, like it as soon as possible, okay? Because that is mandatory. Like this session, hit the like button. I want you guys to increase the likes as of now. I'm counting, okay? Come on, each and every one. It should cross 300 right away. Everyone over here. So we say, according to law of current distribution in parallel combination, it says Q is directly proportional to C. The one which has more capacitance will store more charge. So among these three, 18 has more capacitance, so it will store more charge. So we say over here, listen to me very carefully, my dear friends. Listen to me very carefully. If Q is directly proportional to C, let's suppose, sir, 18 is storing more charge. What will store? Which one will store less charge? Let's suppose X. Obviously, 3 microfarad will store less charge. Let's suppose it stores X charge. Okay. If this is X, This is how many times greater than 3? 3 threes are 9. So if this stores x, this will store 3x. Now, this 18 is how many times greater than 3? You say, sir, 3 6s are 18. 6 times, so this will store 6x charge. So that's what I said. If this stores x charge, 18 will store more charge. How much? We say 6 times of x, 6x. So can I say, sir, if 100 microcoulomb charge is coming from this side, so we say it gets divided in x, 3x and 6x. So we say this x plus 6x plus 3x will be equal to, sir, how much? 100 microcoulomb. So we say this will be 10x is equal to 100 microcoulomb. So we say x is equal to 10 microcoulomb. Means in this particular case, 3 will store 10 microcoulomb. So we say, let's call this as Q1. Let's call this as Q2. Let's call this as Q3. So we say Q1 is equal to 10 microcoulomb. Q2 is how much? We say 3x. And 3x, x is how much? 10. That is 30 microcoulomb. Q3 is how much? We say, sir, 6 into 10. That is 60 microcoulomb. Great, great. 10, 30, 60. 10, 30, 60. In the last slide, which one? I have mentioned the Perler combination only. In the last slide. This one is the series combination. Everything is correct. Is it clear? Is it clear to each and everyone? So guys, we are taking the break right now, okay? In the last slide, you wrote okay. In parallel combination. It is parallel over. Thanks, buddy. I'm not exactly well today. That's why I need some break. Okay, we'll take a break till 8. I'll show you some of the best questions afterwards. Okay, you'll be able to solve each and every single question. Will not leave any damn thing. Break till we say 8. This session will not be too long. We'll finish this by 10 o'clock. We'll finish this by 10 o'clock. Okay, guys, have some dinner. Break till we'll be back. Okay. Show some fire and like this session. Everybody like this session.
All right, people, back to basics. Just a second, just a second. Let the people join and we'll start. Just a second. Okay. Okay, guys. Let's start. Am I audible and visible properly? Let me know in the live chat. Everybody with the fire symbols. Each and everyone. And if you have not liked the session, do like the session as simple as soon as possible. Okay. Now we will solve different categories or the different types of problems over here. As I have told you, we'll be solving each and every single problem type. Okay. So listen to me very carefully. We are done with the series and parlor. Now, let's suppose, great. Let's suppose we have got a combination of capacitors, something like this. And we are supposed to find the net capacitance or equivalent capacitance between A and B. Okay. Now, if I say, for example, we have got a capacitor, something like this C and this C and this C. This is capacitor first, second and third. Three capacitors are in series. And if I ask you to tell me the net capacitance, you'll say, sir, I'll simply use the formula 1 upon C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3 and I'll get the C equivalent. But the case over here is, see, we have got the capacitor C, another C, another C. It looks like they are connected in series, but they are not. Why? Because there is a wire which is basically connected over here and it is from this point to this point and we have connected it somewhere around over here also. And there is another wire which is exactly similar to the above wire. Okay. So these are the two wires which are connected over here. So we say this is not the series combination. Now, in order to solve this type of problem, let me just tell you what you guys are supposed to do. Listen to me very carefully. See. The first and the foremost thing is mark the points. The first and the foremost thing is, in order to solve this category of problem, is mark the points in the circuit. Mark the points in the circuit. Let me just tell you. See, this point over here is A. We say, sir, if I say potential at this point is, we say VA or VB, or sorry, VA, or you say V, or you say A, whatever it may be. Same potential will be exactly over here. We call this as A. Now, if I say what will be the potential at this point, sir, in between this, the capacitor comes, so we cannot say the potential at this point will be A also. No. Okay, so we say over here the potential, if this is A, now this wire is, it's a simple wire. It goes and reaches this particular point. There is no load, no capacitor in between. We say if the potential of this point is A, we say this point will be also having same potential. So we mark it with the same point A, same name A. I hope you got it. Now, come from the another side. This point is having the potential B. We say this point also has the potential B. Now come from this point and reach this point. We say this point will be also having the same potential B. Okay, because this is a simple wire. If I say, sir, there is a capacitor over here also, then you cannot say the potential of this point is equal to the potential of this point. No, because potential, the capacitor came in between.
This is what I have told you. Now you guys tell me one thing. First thing is mark all the points. We are done with the marking. Second is draw the points. Draw the points on the paper. See, how many number of points are exactly present in the entire circuit? You say, sir, A and then B and this B only. This is B. Yes, this B only. Sir, what is the C? C is the capacitance. So we say draw the points on the paper. So we say, sir, let me draw this point A and let me draw this point B. We have only 2 points. Now, sir, if we talk about the first capacitor is connected between A and B. So I can draw it something like this and its capacitance is C. The second capacitor, this one, is also connected between A and B. Sir, this is A, this is B. So we can draw it something like this. So this is also C. The third capacitor, this is B connected between B and A. A and B, B and A, one and the same thing. Sir, this third capacitor is also connected between A and B. One end is A, another end is B. So we can call it something. We can make it something like this. So this will be C. Can we not say in this particular case, this capacitor C, this capacitor and this capacitor, all the three are connected in parallel? Sir, yes. So in case of parallel combination, we say, sir, C equivalent is C1 plus C2 plus C3. So this will be C plus C plus C. So that will be C plus C plus C, that is 3C. So basically, these three capacitors were connected in parallel, not in series combination. How many of you got it? How many of you got it? In the live chat, give me a thumbs up, give me the fire symbols, each and every one. And if you have not liked the session, like it as soon as possible. Then we will move on to the next question. Okay? Let's suppose we have this combination. We have this combination. Can you guys follow this? Can you guys follow this? Can you guys follow this? What is the first thing we are supposed to find? We have got 1, 2, 3, 4, 5, 6 capacitors. Okay? And the wires are connected something like this. This is the first wire, second wire, third wire. And you are supposed to tell me the net capacitance from P to Q, between P to Q, equivalent capacitance. What is the first thing that we do? Sir, in order to solve this question, the first thing that we do is we mark all the points. Let me just tell you over here, boys and girls, let's suppose if this point is P, can I say this point we can call this as P? If this is having some potential, this will have the same potential because this is a simple wire. Now from this point till this point, this is also point P. Same wire, same potential. Yes, sir. Now, okay, let's move on to this point. This is the Q. If this point is having some potential, will this point have the same potential or different potential? Sir, different. Why? Because in between capacitor came. So whenever load comes in between, we cannot say the potential of other end will be same. Keep that thing in your mind. So if this is Q, listen to me very carefully. In this type of question, mark or introduce one more point. Introduce the third point. Sir, we have P, we have Q. Introduce third point. Let's call that X. Let's suppose potential at this point will be something, na? So let's call that potential as X. Now, if this is X, now this is simple wire from this point till this point. So this will also be X. Now from this point till this point, so this will also be X. I hope you got it. I hope this is clear. This is point P, this is point P. So simple wire till over here, this is also point P. Now this is point Q. You cannot say this is also point Q. No, why? Because capacitor is in between. Let's introduce new point. Let's call this as X. So if this is X, so this point will be also X. If this is X, so this point will be also X. Now, drawing all the points are done. What is the second thing that we do? Draw the points over here. Marking all the points is done. Draw all the points on the paper. How many points are there? P, X, and then we have Q. Sir, what is C? C is the capacitance. So we say P, then you have X, and then you have Q. Now, ladies and gentlemen, boys and girls, let me just tell you over here, sir, if we talk about the first capacitor, it is connected between P and X. So let's make it over here. This is connected between P and X. So if we talk about the second capacitor, it is connected between X and P. This capacitor, X and P. So X and P and X, one and the same thing. We can make it something like this. And when it comes to the third capacitor, it is connected between P and X. So we can say it's something like this. This will be P and X. And if we talk about this capacitor, see, this capacitor and this capacitor, these two capacitors are connected between X and X. Whenever, listen to me very carefully, you see a capacitor is connected between same ends. A capacitor is having the same potential from two different ends. From two ends, it is having same potential. So in that case, we say this will short circuit. These two capacitors will short circuit. Sir, what is that? Short circuit. Simply, they will not work, or we say simply remove. Remove them from the circuit. Remove them from the circuit. If you see the potential of this point and potential of this point, see, it is X, it is X. So you can remove them. Okay, short circuit them, remove them. Now, if you remove them, then the final capacitor is this one. This is connected between X and Q. This is connected between X and Q. This is C, this is C, this is C, and this is C. How many of you got it, boys and girls? How many of you got it? Let me know in the live chat. Now see, sir, over here we can clearly see that these three capacitors are connected in parallel. So we say they have the equivalent capacitance of, sir, C, C, C. In parallel combination, it is C1 plus C2 plus C3. So this will be 3C. And then you have this C. Now these two this is the equivalent capacitance. See, this is point P and this is point Q. This is 3C. Instead of this, I'm writing 3C and this is C. Now this 3C and C, they are connected in series. And how do we find the equivalent in series combination? In case of two capacitors, I have shown you the formula. In case of two capacitors, we'll write the formula directly. This is the formula. C equivalent for two capacitors in series, C equivalent is C1 C2 upon C1 plus C2. C1 C2 upon C1 plus C2. C1 C2 upon C1 plus C2. So I say over here, C equivalent is equal to C1 C2 upon C1 plus C2. What is C1? That is 3C into C2 is C upon 3C plus C. So this will be 3C square plus 4C. C and this, so this will be 3C by 4. How many of you got it 3C by 4? Great, great, great. 3 by 4C. Great, great, great. Let's move on to the next one. Okay. Can you tell me what is the... You guys are supposed to tell me this is... Find C equivalent in this particular case. This is C, this is C, this is C, this is C. Tell me what is the value of C equivalent in this case? What is the value of C equivalent in this case? Each and everyone, let me know in the live chat. All the people out there. Find C equivalent across AB. See, I'll tell you how to solve this particular question. Sir, this is point A. If this is point A, this will be also point A because this is the same wire. And from this point to this point, the wire is same. This is also point A. Now you guys tell me one thing, sir. If this is point B, this is also, sir, point B. Now see, sir, this capacitor and this capacitor, both these capacitors are connected between same points. So this potential is equal to this potential. We say these two will short circuit. So we can remove them. So remove them. Now what remains? This capacitor, this capacitor. How many points are over here? A and B. Only 2 points. So just write A and B. Sir, first capacitor is between A and B. This one is C. And this capacitor is also between A and B. This is C. C and C in parallel. So C equivalent will be 2C. Guys, is this clear to each and everyone? I need to know. Great. Next question. This was asked in NEET 2021. We have got a capacitor over here. We have got a capacitor over here. And we were supposed to find in this particular case the equivalent capacitance of this system. We have got capacitance C, okay? And we have got this. Now in this particular case, you guys are supposed to tell me the net capacitance. See, how do we solve this particular question? First and the foremost thing is mark the points. Let's suppose this is the point A. Let's suppose this is point A, okay? So this end is connected to point A, this end is connected to point A. This capacitor is having one end connected to point A, this capacitor is one end is connected to point A. Now let's suppose this is point B. Let's suppose this is point B. Let's suppose this is point B. Can I say in this particular case, sir, this end, this capacitor, this end is connected to point B, and over here from this point to this point, if this is point B, this will be also point B because this is a simple wire. So from this point to this point, this is a simple wire, so this will be B. So this capacitor is connected between B and B, so we can short circuit it, we can remove it. So what remains? This capacitor and this capacitor. Now this capacitor is connected between this one, A, this is A and B. This is connected between A and B. And this lower one is also connected between A and B because this is A, this will be A. So two capacitors, something like this. This is C, this is C. This is A, this is B. A and B. So this will be 2C. Answer is 2C. Great, 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 great. Is it clear? Is it clear? Can you solve this question? We have got a capacitor over here. We have got a system. Something like this. This is 2 microfarad. This is 3 microfarad. This is 6 microfarad. And in this particular case, this is a battery we have. This is 2-volt battery. The energy stored in the condenser. You guys are supposed to tell me how much is the energy stored in this entire system. How much is the energy stored in this entire system? We have got 3 microfarad capacitor. We have got 6 microfarad. We have got 2 microfarad. I'm making it over here. The one, if it is not visible to you, I have made the entire diagram over here once again. This is 3 microfarad, 6 microfarad, 2 microfarad, and 2-volt battery is connected. You guys are supposed to tell me how much is the energy stored. See, this battery will store the energy in these capacitors. How much is the energy stored in the capacitor? How much is the energy stored in this system? Sir, we know energy stored is 1 by 2 CV square. Yes, sir. Now, what is the value of C that we have to take? C is the C equivalent in this case. What is the net capacitance of this system? You guys tell me one thing. Sir, this capacitor and this capacitor, both are connected in series. Both are connected in series. Both are connected. 3 and 6 are connected in series. Can you tell me, sir, when it comes to CC, first and the foremost thing is we'll find the value of C equivalent. We'll find the value of C equivalent. We say, sir, over here, equivalent of P and we say 6. 3 and 6 are connected in series. How to find? We say, sir, C equivalent in series is C1, C2 upon C1 plus C2. We'll find the equivalent of these two first. Sir, that is P into 6 upon 3 plus 6. How much is that? Sir, this will be 18 upon 9. That is equal to 2. Means equivalent of this and this is nothing but 2 microfarad. Now see, this 2 microfarad, I'll make the circuit once again. Now it will be, instead of these two, I'll make the 2 microfarad. And then we have this 2 microfarad. And then we have the battery over here. This is 2 microfarad. This is 2 microfarad. And this is 2 volt. Now, sir, this 2 and this 2 are in parallel. 2 plus 2 is 4. So we say C equivalent is nothing but 4 microfarad. Now, can you find the value of energy? 1 upon 2 into this 1 by 2. C equivalent. Instead of C equivalent, I'll write 4 and V square. V square is, we say, 2 square. And 2 ones, 2 twos. U is equal to, so this will be 4 into 2 is 8 microjoule. How many of you got the 8 microjoule? Yes. Is it clear, guys? Is it clear to each and everyone? Let me know. Yes, 8. Guys, let me know in the live chat, then only I will move forward. Give me the signal. Give me the signal. Is it clear? With the fire symbols. Okay. Now we have got the next topic, that is what we call the dielectric in capacitors. Great, great, great. We'll talk about the dielectric in capacitors now. Listen to me very, very, very carefully. See, let's suppose we have got, this is very important, okay? Each and everyone. In JEE 2021 mains, questions were directly came from this particular topic. So listen to me very carefully. Let's suppose we have the parallel plate capacitor. Let's suppose we have a parallel plate capacitor over here. Okay, this is a parallel plate capacitor. Cool. And on this parallel plate capacitor, we say on this particular plate Q charge is present, positive charge. And on this one, my negative charge is present. We say this is minus charge. Cool. Okay. Sir, how does this charge come over here on this particular plate? We say, sir, we connect a battery over here. Battery will take charge from one plate and will place it onto the another plate. So positive charge gets occupied on this one and negative charge gets occupied on this one. This is a parallel plate capacitor. Cool. Now, listen to me very carefully. If I say Q charge is present on the plate of the capacitor. Yes, sir. Q charge is present. You guys tell me one thing. Sir, we know this positive attracts this negative towards itself. This negative will also attract this positive towards itself. Yes, sir. So when the two forces, when these two plates attract each other, so they will come close and they will stick to each other. So when they stick to each other, there will no longer be the separation between the two plates, means they will no longer remain a capacitor. So it will not behave as a capacitor. Why? Because capacitor is when two plates are parallel to each other at some separation distance between them. If they are attracting each other, so they will stick to each other, means there will no longer be the separation. They will no longer behave as a capacitors. Okay, yes. So what we do is that we say here two plates will attract each other. Here two plates will attract each other. So they stick to each other. They no longer behave as a capacitor, because there will be no separation. So to overcome this problem, I'll just write over here, overcome this problem. So to overcome this problem, we use dielectrics. We use dielectrics. Means, sir, we do not want these two plates to stick to each other. What we use is that we use dielectrics in between. We use dielectrics in between. So we'll be using the dielectric in between. Sir, what is a dielectric? Dielectric is a material. Like you have conductors, you have insulators. Similarly, you have dielectrics. This is a dielectric. So why do we use dielectric? Because this plate should not stick to this plate. Okay, there should not be instability. It should remain stable. It should become yes, 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 yes. So we say in simple language, I am saying. So we say over here, listen to me very carefully. Now, this plate is having the positive charge. This plate is having the negative charge. Now, if I say, sir, dielectric will be also having some charge. Okay, it will also have its own charge, positive as well as negative. Now, you guys tell me one thing. This positive plate will attract the negative charge of dielectric. Dielectric has positive charge as well as negative charge. So negative charge of the dielectric will be attracted towards the positive plate, and positive charge of the dielectric will be attracted towards the negative plate. So there will be charge separation inside the dielectric. Okay, I hope this is clear. I hope this is clear. So we say, sir, if charge present on the plates is Q, now charge gets occupied on the dielectric also, on this side, from this side, negative charge, from this side, positive charge. And this is what we call the QI, induced charge. So we say, to overcome this problem, we use dielectrics. So we say, in this particular case, we say QI is the charge induced on the dielectric. Okay, so what I'm trying to say is that we have a positive plate, we have a negative plate. We are placing a dielectric in between. The positive charge of the dielectric gets attracted towards the negative plate. The negative charge of the dielectric gets attracted towards the positive plate. Now, this charge which is occupied on the dielectric is called QI, and this QI is called induced charge, and this Q is called the charge placed on the plates. Now, in NEET 2020, in JEE 2021, they asked that what is the value of this QI? And let's suppose this dielectric has a dielectric constant K, because every dielectric has a dielectric constant, and we have over here it is K. So we say to find QI, just remember the expression directly. If somebody asks you what is the value of this QI, we say this QI is nothing but induced charge is nothing but that is Q. Q is the charge on plates, 1 minus 1 divided by K. Okay, where Q is the charge on plates and K is dielectric constant. K is a dielectric constant. Is it clear to each and everyone how much charge is induced on the dielectric? Yes, sir. Now, sir, we know how much the charge is induced on the dielectric. We got that. Can you tell us what is the induced charge density? Sir, what is that? Let's suppose this is having the sigma I. Charge per unit area. On unit area, how much charge is induced? This is the total charge, QI. On unit charge, how much charge is induced? On unit area, how much charge is induced? That is QI. and this will be having the charge density of sigma. That is charge density. Now, let's find the induced charge density. The induced charge density means sigma I. See, sir, we know sigma is equal to, that is nothing but Q divided by A. So from here, can we write, sir, take this over here, we say Q is equal to sigma into A? Yes. Now from equation first, let's call this as equation first. From equation number first. From equation first, can we just write, instead of Qi, I can write, sir, sigma I into A. Yes, sir. We say Qi is equal to sigma I into area is equal to, instead of this Q, we can write, sir, sigma into A, because Qi, sigma I, area will be same. Dielectric is having the same area as the area of plates over here. And then we have 1 minus 1 divided by K. Can I just say, sir, A and A will get cancelled out over here. So from this one, we say sigma I is equal to sigma into 1 minus 1 divided by K. So this is what we call the induced charge density. This is what we call the induced charge density. This was asked in JEE mains 2021, charge per unit area. Is it clear? Is it clear, guys? Let me know in the live chat. Is it clear? Is it clear, guys? Is it clear, each and every one? Clear, guys? Yes. Cool, cool, cool. So this is the induced charge density. So inside the dielectric, when you place the dielectric between the plates, we say negative charge is occupied over here, positive charge is occupied over here. How much is that charge Qi? So that charge occupied is nothing but Q. Q is the charge on plates, 1 minus 1 by K. K is the dielectric constant. Every dielectric has a dielectric constant. Okay, K. For air, K is equal to 1. So we say for a conductor, K is equal to infinity. And induced charge density will be this much. Now let's move on to the next one. This is also important. Battery remains connected during insertion. What does this mean? Let me just tell you over here. Let's suppose you have a parallel plate capacitor over here. Let's suppose you have a parallel plate capacitor over here. Okay, yes. Now we are connecting a battery to this parallel plate capacitor. Listen to me very carefully. I'll give you the feel of this topic also. We are connecting a battery to it. We say, sir, battery will occupy positive charge on this plate and negative charge will be occupied onto this plate. Yes, sir. Battery will occupy positive charge over here. Negative charge will be occupied onto this plate. Okay, sir. As simple as that. Now you guys tell me one thing. Sir, this capacitor has got charge Q on it. So this capacitor has the capacitance C. Yes, sir. 110%. Now, have I inserted or placed any sort of dielectric in between these two plates? As of now, we say no. So we say this is nothing but before insertion. Before insertion. Sir, what does before insertion mean? Before insertion means if you have got a capacitor, you connect a battery, you have not inserted the dielectric as of now. You will insert the dielectric later on. That is after insertion. But before insertion, sir, before insertion, let's discuss some terms. Let's discuss some terms. What is that? First one is, sir, before insertion, the capacitance will have some value over here. Yes, we say this capacitor has capacitance. Sir, it has capacitance. We call that C. Sir, before insertion, this is a battery. It is giving potential difference V to this one. So we say it has potential difference. That is nothing but a V. And sir, this battery is storing charge on it. Yes, sir. Sir, Q charge is being occupied on this one. So we say charge stored in the capacitor is nothing but we say Q. And we say Q is equal to CV. We have studied this formula. Yes. Now you guys tell me one thing. Sir, before insertion, positive charge is over here, negative charge is over here. I have told you electric field is always from positive charge towards negative charge. So before insertion, electric field will have some value. Yes, sir. Sir, what is that? Sir, electric field is, remember this formula directly. Electric field is equal to potential difference divided by V by D. D is the distance between the charges or distance between the plates. If you have to find the electric field, that is V by D. V by D. V is the potential difference. D is the electric field. D is the distance. And if you say, sir, energy stored, U is equal to 1 by 2. Or if you have, guys, if you have stored charge on it, means you have stored energy. How much is the energy stored? Energy stored. So we say U is equal to 1 by 2 C V square. Is it clear to each and everyone? Is it clear to each and everyone? Is it clear to each and everyone? This is before the insertion. Now what we are doing that, what we'll do is that we'll insert a dielectric after insertion. We say after insert. After insertion. Let's suppose this is positive plate, same positive plate of the capacitor, and we are connecting a battery to it. Okay. Now what we are doing is that we'll insert a dielectric over here. We'll insert a dielectric over here. This is dielectric. Okay. And it is having the dielectric constant of K. We can call it ER also. So this is positive plate and this is your negative plate. Okay. Now what we have to learn in this particular case is that if we insert the dielectric between the plates, but battery remains connected. Did I disconnect the battery? No. Battery remains connected during insertion. I am inserting the dielectric, but battery remains connected. Battery is not disconnected. So we say battery remains connected. Battery remains connected. So we have to see what happens to the capacitance. First and the foremost thing. Before the insertion, this was the value of these different terminologies. Let's see after insertion what's going to happen if battery remains connected. First of all, let's say, sir, new capacitance will be C dash. Sir, what happens to the capacitance? If you insert the dielectric between the capacitor, between the plates, sir, will that capacitance remain same or change? Remember it always changes, that it increases by K times. C is the initial capacitance before insertion and C dash is the new capacitance and K is the dielectric constant. So K times it increases. And sir, when it comes to potential difference, we say, sir, battery remains connected. So the work of battery is to maintain the potential difference. So we say potential difference V dash will remain same because battery maintains potential difference. Battery is connected over here. And then charge, we say charge Q dash, new charge, because battery is connected. Battery only stores the charge. It keeps on taking the charge from one plate to another plate. So Q dash is equal to C into V. C dash into V dash. So we say, sir, C dash is how much? K times of C. V dash is how much? That is V. Now see, K times of CV. CV, what is CV? CV is Q. So instead of this CV, I'll write K times of Q. Okay, so we say Q dash is equal to K times of. Now, next, this is Charge, let's talk about the electric field. Sir, electric field E dash, new electric field, is equal to V dash divided by D dash. That is new potential difference divided by new distance between the plates. Sir, distance between the plates is D only, it remains same. And potential difference is also same, that is V by D. So that is E only. So potential, that electric field remains same. Sir, energy, U is equal to U dash, new energy, 1 by 2 CV square. Instead of C, we say C dash into V dash square. So we say 1 by 2. C dash. C dash is K times of C. V dash is V only, V square. See, take this K out. We can say, sir, K times of 1 by 2 CV square. And 1 by 2 CV square is what? That is initial energy U. So we say this is nothing but K times of U. So we say U dash is K times of U. We say energy also increases by K times. How many of you got this analogy? Everyone. Give me the thumbs ups in the live chat, guys. If not, I'll not move forward. Everyone, send me the fire thumbs ups. Is it clear? Is it clear to each and everyone? Like the session, the one who, if you're not like the session as of now, like the session as soon as possible, guys. Mark the attendance. Okay, great. Let's move on to the next one. We have this. Now, this was the case when battery remains connected during insertion. Now, we'll talk about the case when battery is disconnected. Battery is disconnected during insertion. Now, let me just tell you. I'll write over here. Let's suppose we have the parallel plate capacitor. Okay. And this is the battery over here I am connecting. So, it will place the charge positive over here, negative charge over here on this one. And we say initially before insertion, battery is connected only. Now, during insertion and once we place the dielectric, we'll disconnect the battery. So we say over here, capacitance of this capacitor is C. Okay. And you guys tell me one thing. Then we have charge. Charge is nothing but Q. Charge stored on this is nothing but Q. Potential difference is V. And we say V is equal to Q divided by C. Because Q is equal to CV. Yes, sir. Now you guys tell me one thing. Sir, electric field is V divided by D. Sir, energy. Over here we'll write energy, another form of energy, that is nothing but Q square by 2C in terms of Q and C. Previously, I took 1 by 2 CV square, one and the same thing. Now, what I'll do is that after insertion, I'll remove the battery. So, let's suppose this is one plate, this is another plate, and I have placed the dielectric in between. This is dielectric, and its dielectric constant is K. And now I have removed the battery. See, I have removed the battery. No battery is mentioned. Over here, battery is connected. Now, in this particular case, I have removed the battery. Okay, I have removed the battery. Now, let's talk about the capacitance after insertion. Let's talk about the capacitance. See, after insertion, if we talk about the capacitance, listen to me. We say, sir, C dash, capacitance final, that is C dash. Even if the battery is connected or battery is removed, once you place the dielectric, capacitance always increases. We say K times, dielectric times. Okay, even if the battery is connected or disconnected, it doesn't matter. Now, let's talk about the charge. We say, sir, charge Q dash is equal to. Now listen to me very carefully. We know, sir, when it comes to the battery, battery stores the charge. It takes the charge from one plate to another plate. Now, if you disconnect the battery, charge stored on the plates will remain same now because battery is disconnected. If you again connect the battery, it will again store more charge. Now, if you disconnect, it will remain as it is. It will remain the same. So we say charge Q dash is equal to Q. Charge initial is equal to finally charge will remain same. It will no longer increase. Now, if we talk about the potential difference V dash, we say, sir, V dash is equal to Q dash by C dash. Sir, Q is nothing but Q dash is Q because charge remains same. C dash, sir, C dash increases. C dash is K times of C. Sir, Q by C. What is Q by C? We say Q by C is V. Sir, charge upon capacitance is V. So we say V dash is equal to Q by C. It is nothing but V divided by K. V divided by K. I hope this is clear. I hope this is clear. Okay. Then you have electric field. Sir, electric field is V divided by D. Final electric field is E dash, V dash, D dash. Now you guys tell me one thing. V dash is V by K. So this is V divided by K. And D dash is D only. Now V divided by D. Boys and girls, what is V by D? V by D is E. So if V by D is E, so this is E divided by K. Means electric field has decreased by how many times? K times. E dash is equal to E by K. And then you have energy. We say U is equal to Q square by 2C. Sir, final energy when battery is disconnected, sir, it will be U dash. U dash is equal to Q dash square upon 2C dash. Final charge upon final capacitance. Sir, it will be nothing but Q dash. Q dash is nothing but Q square upon 2 into C dash. C dash is K times of C. K times of C. Take this out. You say, sir, Q square upon. This is K into 2C. So this will be U dash. This will be U dash. Q square by 2C. Sir, Q square by 2C is U. Now Q square by 2C. Instead of Q square by 2C, I'll place U. So U dash is equal to U divided by K. So energy has been decreased by K times if you disconnect the battery. Potential has been decreased by K times if you disconnect the battery. Why? Because battery maintains the potential difference. And in this particular case, we see, sir, energy has been increased by K times. Okay. Sir, why? Because battery remains connected. Battery is the only thing which does the work and stores the energy. That's why over here energy increases K times by K times. Charge increase by K times. Over there it decreases. Is it clear to each and every one, guys? With the fire symbols, Is it clear to each and every one? Then we'll move on to this one. Guys, I need to know in the live chat only. Yes, everyone. Great. Okay. Okay, great. Great. Now we have the series combination of a dielectric. Okay. Sir, what is this? I'll tell you. See, let's move on to this one first. This will give you the feel. Now see, or I'll show you it over here. Now see, let's suppose we have a plate. This is a positive plate over here of a capacitor. Okay. And then we have the negative plate of a capacitor. Yes, sir. This is a negative plate of the capacitor. What I am doing is that I'll place a dielectric in between the capacitor. This is the first dielectric. I'm not placing only one dielectric, but I'll place multiple dielectrics. This is the first dielectric. Let's call it K1. I'm placing another dielectric. Let's call this K2. I'm placing one more dielectric. Let's call this K3. This is the width of this one. This is the width of this one. This is the width of this one. So I'm placing 3 dielectrics in a row or in series. Now this is what we have to study right now. Placing multiple dielectrics between the plates. So this is what we call the dielectrics in series. This is what we call the dielectrics in series. I hope you got the feel of this one. That's what is mentioned over here. This is the first case. Sir, in this particular case, we are taking a plate. This is a plate on which positive charge is present. Yes. And I'm taking another plate on which negative charge is present. This is another plate, negative charge is present. And I'm placing a dielectric. This is the dielectric in between the 2 plates. Now, distance between the 2 plates is given as a D over here. This is the D. Okay. And the width of this is T. The width of dielectric is T. And dielectric constant is K. Dielectric constant is K. Now you guys tell me one thing. In this particular case, here, dielectric of width T is placed between the plates. The dielectric of width T is placed between the plates. To find, so capacitance of capacitor changes. Sir, how? Because I told you whenever we place the dielectric between the plates of a capacitor, its capacitance changes. So we say over here, its capacitance changes, its capacitance changes once you place a dielectric. We have to find that capacitor. To find that new capacitance. Now listen to me very carefully. If we find that new capacitance, all the people out there, listen to me very carefully. Sir, that new capacitance will be C equivalent is equal to. C equivalent is equal. We say epsilon naught A. Sir, what is A? A is the area of the plates. A is the area of plates. Upon. Then you have D. D is what? D is the distance between the plates. Minus, then you have minus T. What is T? T is the width of the dielectric. D minus T. D is the distance between the plates. T is the width of the dielectric. D minus T plus. Then you have T divided by K. Sir, T is the width divided by K. K is the dielectric. You have to remember this, guys. You have to remember this. We don't have to derive. If somebody asks you, if somebody asks you, I'm placing a dielectric of width T in between the plates to find the capacitance of this capacitor. So that capacitance will be epsilon naught A, D minus T plus T by K. Remember it directly. Now the question over here is, when the dielectric is replaced with the air, then find its capacitance. It is saying that we have the same 2 plates over here. And you are placing this dielectric in between the 2 plates. This width is given as D. This is given as T. But this is nothing but, we say air. For air, dielectric constant is 1. In this case, find the new capacitance. We say, sir, new capacitance will be, if you place the dielectric which is of air. It is, sir, what is dielectric made of air? It is nothing. Okay, we are just considering a dielectric slab, which is just air. It is in reality, it is just nothing over here. C is equal to, we'll use the same formula, that is epsilon naught A upon D minus T and then plus T divided by K. Now in this particular case, what is the value of K? Value of K is 1. So we say, sir, C is equal to epsilon naught A upon D minus T plus T, because this becomes 1. T and T will get cancelled out over here. C is equal to epsilon naught A divided by T. I guess this was the capacitance of a parallel plate capacitor. Yes. Yes. So that is what I'm trying to say over here. If you place a dielectric slab of air, it is like you are not placing anything. It's one and the same thing. Means it is just a parallel plate capacitor. And for a parallel plate capacitor, capacitance is epsilon naught A by D. I hope this is clear. Okay, next is, if the dielectric slab is very thin, let's suppose we have a capacitor over here. Okay, we have a capacitor over here, and you are placing, the distance between this is basically D. You are placing a dielectric slab in between these two plates, but this T is approximately equal to 0. This is very thin. This is extremely thin. Approximately 0 compared to this D. To find its capacitance, we say, sir, C is equal to epsilon naught A upon D minus T plus T divided by K. This is the general expression. Now over here, value of T is 0. Okay. Value of T is how much? We say, sir, 0. This will be 0. So in this case, this will be also epsilon naught A divided by D. Okay. If you are placing something, if you are placing a dielectric in between, which is extremely thin, it is like you are not placing anything, because this is extremely thin. So that's why we say C is equal to epsilon naught A by D. Okay. Then you have next one. Over here. When dielectric is a conductor, if you are placing, let's suppose you have got one plate, you have got another plate. Okay. Now distance between the plates is a D over here. And the dielectric slab which you are placing in between of width T, this is a conductor. For conductor, we say dielectric constant is infinity. So this is nothing but conductor. Now in this case, you guys are supposed to tell me what is the capacitance. We say, sir, capacitance C is equal to epsilon naught A upon, we say D minus T upon plus, we say T divided by K. Okay. Now we say T by infinity, 0. We can remove it. So this capacitance will come out to be, that is epsilon naught A upon D minus T. Okay. Because for a conductor, we say, for a conductor, we say K is equal to infinity. Is it clear, guys? Just a second, I'll get some water. Okay. So is it clear to each and everyone, guys? Let's move on to the next one. Okay. Now if you have the question something like this. Sir, we have got a capacitor over here. This is a positive. This is, I'll make it once again over here. Sir, we have got one plate. We have got another plate. This is the positively charged plate over here. And this is negatively charged plate over here. And in this particular case, we are placing two dielectrics. Let me make it with this one. We are placing, this is first dielectric and this is the next dielectric. This is the next dielectric I am placing. I am placing the two dielectrics over here. And the dielectric of constant is K1. This has the dielectric constant of K2. This position. We say this is Q1, we say this is K1, and this is exactly K2. Listen to me very carefully. This is K1, this is K2. And this distance is given as over here, that is a D. Okay. Now, the width of this dielectric, let's suppose this is given as over here. We say, sir, T1. The width of this dielectric, let's suppose this is given as T2. Okay. Listen to me very, very, very carefully. Sir, we have got a positive plate, we have got a negative plate. Distance between the plates is D. This dielectric is having the width of T1. This dielectric is having the width of T2. This has the dielectric constant K1. This has the dielectric constant of K2. Now, in this particular case, we are supposed to find its capacitance. To find its new capacitance. Sir, why do you call it new capacitance? Because whenever we place the dielectric in between the plates, the capacitance, we say changes. We have to find the new capacitance. So we say over here, this capacitance will be, remember this, sir, epsilon naught A, epsilon naught into A. A is the area. Okay. Epsilon naught A upon, then you have, sir, what is the width of this one? That is T1. So we say, sir, T1 divided by, what is the dielectric constant of this slab? We say, sir, that is K1. So we say T1 by K1. Then you have plus, what is the width of this one? Sir, you say T2. And what is the dielectric constant of this one? That is, sir, K2. So this will be the capacitance in this case. This will be the capacitance in this case. Epsilon naught A upon T1 by K1 plus T2 by K2. This is the capacitance. If you have two slabs, one is having the T1 width, another one is having the T2 width. Okay. This is having dielectric constant K1. This is having dielectric constant K2. Now, over here, and remember this one, first one, which I have shown you over here. If you have a dielectric slab, something like this, this is having the capacitance of epsilon naught A, D minus T plus T by K. Okay. Now let's move on to the next one. Let's suppose if a question is something like this. See, you have got a plate over here which is positively charged. Okay, this is a positively charged plate. And you have got a plate over here which is negatively charged plate. And in between this plate, we have, let's suppose the distance between the plates is D. This slab, this is a first dielectric. This is another dielectric slab. This is another dielectric. And this is another dielectric. It is having the dielectric constant K1, K2, K3, K4. This width is nothing but D1. This is D2. This is D3. This is D4. To find its capacitance, how do we write? We say C is equal to epsilon naught A. A is the area of plates upon. Then you have its width, that is a D1. D1, either you say T1, one and the same thing. So D1 upon. Then you have, sir, K1 plus this width divided by its dielectric constant. We say, sir, D2 upon K2. Then plus its width, that is, sir, D3 upon K3. Then you have plus its width, that is D4 upon, we say, K4. This is the capacitance. This is the capacitance in this particular case. I hope each and everything is clear and sorted over here. Okay. Let me know in the live chat, guys, if this is clear to each and everyone. Guys in the live chat. And also. See. Okay, great. Now see, in this particular case, see, sir, you have told us if we have a capacitor, if we have another capacitor, if we have another capacitor. Sir, these three capacitors are in series. We know how to find their C equivalent. Even we have studied this also. If we have a resistor, another resistor, another resistor. These three resistors are in series. We know how to find their equivalent resistance. Sir, we have studied this. Sir, don't you think over here, this dielectric slab K1, this another dielectric K2, K3, K4, all these dielectrics, they are also in series. So they will also have their equivalent dielectric. Yes, sir. Equivalent dielectric constant. Yes, sir. Now, remember, these slabs slash dielectrics are in series. So they will have K equivalent. Like we have C equivalent, C net, or R equivalent, resistance equivalent. Similarly, we have over here K equivalent. And what is the value of K equivalent in this case? We say, sir, this K equivalent will be, listen to me very carefully. Instead of all these dielectrics, if you want to replace it with one dielectric, which has K equivalent dielectric constant, K equivalent is D. What is D? D is the distance between the plates. D upon, we say over here, that is D1 divided by K1 plus D2 divided by K2. Then we have plus D3 divided by K3. Then we have plus D4 divided by K4. I hope this is clear to each and everyone. Is this clear? Instead of all these dielectrics, we can say, sir, it will be having the equivalent dielectric constant, that is K equivalent. Sir, what is this? This is the capacitance. This is the net capacitance of this capacitor, and this is the K equivalent. Net dielectric constant of these dielectrics. Is it clear, guys? I just need to know. Different people are chatting over there about different stuff. Guys, in the live chat, is it clear to each and everyone? Give me the signal. Yes, great. Now, this was the question which was asked in J Mains 2021. If you guys can solve this question, I'll show you. I'll make it over here. Let's suppose we have got a capacitor. The question was something like this. We have got a polar plate capacitor in which three dielectrics are placed. Okay, three dielectrics are placed. This was basically one plate. Let's call this as one plate, and this is another plate. Over here, three dielectrics are placed. This dielectric is K, this is 3K, this is 5K, and this distance is a D, this distance is 2D, and this distance is 3D. This distance is 3D. You guys are supposed to tell me, find net capacitance. Find net capacitance in this case. This distance, the dielectric first one, it is having the width of D. This is having the width of 2D. This is having the width of 3D. You guys are supposed to tell me what is the net capacitance of this. What is the new capacitance? What is the capacitance of this one? Can you guys solve this? It is very simple if you use the formula I have told you. Okay. See, we say, sir, C is equal to capacitance of this is equal to. We know, sir, Capacitance, if the slabs are placed in series, we say, sir, it is nothing but epsilon naught A upon, we say D1 by K1, T1 divided by K1 plus T2 by K2 plus T3 by K3. Yes, sir. Now we say C is equal to, I'll just write it over here. We say C is equal to epsilon naught A. A is the area. Now T1, T is the width of first dielectric, that is given as D. That is given as D upon. And T1 by K1. What is the K1? K1 is the dielectric constant of this one, that is K. Then you have plus. We say T2. T2 is nothing but 2D upon K2. What is K2? That is 3K, dielectric constant of this one. Then you have width of this one plus, that is 3D upon width of this one. Just a second. We say 3D upon, we say 5K over here. Okay. Then you have epsilon naught A upon, in this particular case, what should we take common over here? We say, sir, D divided by K. So what remains? This is 1 plus, we say, sir, 2 by 3. In this particular case, then we say, sir, 3 divided by 5. Because see, in these three, what is common? D by K, D by K, D by K. I'm taking D by K common. Okay. And then what remains? 1 plus 2 by 3. And if you solve this, it will come out to be epsilon naught A upon. So this will be D divided by K. And if you solve this, this is nothing but, we say that is 34 divided by 15. This is 34 divided by 15 if you solve it. Okay. And then I can write it over here. C equivalent is nothing but epsilon naught A. See, this is epsilon naught A, D by K upon, we say D divided by K, and then we have 34 divided by 15. If you take this 15K in the numerator, so C equivalent will be 15K epsilon naught A upon 34D. This is the answer. This is the answer. This is the answer. You just have to you just have to apply one single formula in order to solve this question. You just have to apply one single formula in order to solve this question. Is it clear to each and everyone, guys? Make sure you have liked the session. Is it clear? Or shall I show it once again? Okay. Then we have, if this is clear, then we have one more question on the same pattern. This was also asked in J Mains 2021. Let me just show you what does the question say. The question says that we have got a parallel plate capacitor, and in this case we have placed a dielectric in between. Okay, this is the dielectric over here. This is the dielectric, and it has the dielectric constant of K, and this width is given as 3D divided by 4, and this is placed over here air, and then this width will be how much? That is a D by 4, because total distance is D. In this question, we are given a parallel plate capacitor. Yes, sir. This is one plate, this is another plate. Okay. And if this is, let's suppose, positive plate, and this is, let's suppose, negative plate, and in between I have placed two dielectrics. One is K, it is width is having 3D by 4, and another one is air, and it is having D by 4, and we know for air K is equal to 1. Find its equivalent capacitance. At least you guys can try this. This is very simple, very simple. At least you guys can try this. At least you guys can try this at your own. Can you guys solve this particular question over here? See. Sir, we'll use the same formula once again. C is equal to, whenever we see two dielectrics placed in series, we say C is equal to, then we have epsilon naught A upon, we say D1 by K1, plus we say D2 by K2, then we have plus D3. Okay, we have only two dielectrics over here. We'll use this formula. Okay, fine. Now in this case, we have epsilon naught A upon. Then we have D1. What is the value of D1? That is, sir, D divided by 4. D1 is the width of this one. That is D by 4. That is D by 4. Upon K1. Sir, what is the value of K1? K1 is 1. Sir, D1 by K1. K1 is 1. Okay, then plus. D2. What is the value of D2? That is the width of this one. We say this is 3D divided by 4. And what is the value of K2? K2 is K. So I'll write over here 4K. Now, can we simplify this? So this will be epsilon naught A upon. So we say in this particular case D by 4. So what remains? 1 plus 1 divided by K will be over here. 1 plus 1 by K. Now, we can write this C will be epsilon naught A upon. Epsilon naught A upon. We can say D by 4. We can say over here. We can say over here D by 4. 1 plus 1 divided by K. If we cross multiply it, so we can say C is equal to epsilon naught A upon. We say D divided by 4. And this will be K plus 1 divided by K. Now take this 4K in the numerator. So we say, sir, this 4K in the numerator, this will be epsilon naught A into 4K upon. We say, sir, D into K plus 1. Now you guys tell me one thing. This epsilon naught A by D, this was C dash, C dash, C dash. C dash is the new capacitance after placing the dielectric. Now, sir, without dielectric, we know the capacitance of a parallel plate capacitor is epsilon naught A by D. So instead of this, can we just write C dash is equal to, we say, sir, C naught. It is given. So this is 4K upon K plus 1. Is it clear? Is it clear? Is it clear, guys? Everyone. I just want to know in the live chat. I just want to know in the live chat. Then I can move forward. Then I can move forward. Is it clear to each and everyone, guys? Okay, is it clear to each and everyone? Great. Show some fire, guys. Okay. Now, parallel combination of dielectrics. Parallel combination of dielectrics. Let me show you over here. See, previously, I told you, if I have a plate over here, if I have another plate over here, we were placing the dielectrics something like this. This was basically the series combination of dielectrics. Now, if I show you what is the parallel combination of dielectrics, let me just show you over here. See, these are the two plates. If I say these are the two plates I'm having over here, these are the two plates I'm having over here. Sorry, these are the two plates I'm having over here. Okay. Now, in this case, if I have to place dielectrics in parallel, is it visible? No, it is not visible at all. Just a second, I'll show you. I'll switch on the lights for a second. If I say, let's suppose these are the two plates I am having. Okay. This is positive plate. This is negative plate. Now I have to place dielectrics in series. I'll place one dielectric, something like this, another. Now, if I have to place the dielectrics in parallel, I'll place 1, 2, 3, 4, something like this. This will be parallel combination. This will be series combination. I hope it is clear. I hope you got the feel. I hope you got the feel. I hope you got the feel. Now, I hope you got the feel. Now see, same is the case exactly over here. This is the positive plate. This is the positive plate of the capacitor. This is the positive plate. Okay. And this one is the negative plate of the capacitor. This is the positive plate. This is positive plate. And this one is negative plate. Now in this one, we have placed the 3 dielectrics. Let me show you with this color. Sir, this one is the first dielectric, that is K1. Sir, this one is the next dielectric, that is K2. This one is the third dielectric, 1, 2, 3. The 3 dielectrics in this particular case are placed in parallel, K1, K2, K3, K1, K2, K3. And the width of this one is given as, we say, sir, this is nothing but A1. This one is given as A2. This one is given as, we say, A3, width of this dielectric. All the 3 dielectrics and separation between the plates is given as a D. I hope this is clear to each and every one. Separation between the plates is given as a D. This width is A1, A2, A3. This is D. Now in this case, if you have to find here also dielectrics are placed between the plates. So its capacitance. Its capacitance will increase. We know, sir, whenever you place the dielectric in between the plates, the capacitance of the capacitor increases, that's for sure. So we say, sir, this capacitance over here will be, in case of series, it was epsilon naught A upon D1 by K1 plus D2 by K2 plus D3 by K3. But over here it will be epsilon naught divided by D. So D is the distance between the plates. Then you have A1. A1 is the width of first dielectric into K1. K1 is the dielectric constant of first dielectric. Then you have plus A2. A2 is the width of second dielectric into K2. K2 is the dielectric constant of second dielectric. Then plus, we say A3 into we have K3. So this is the dielectric constant of 3. This is the dielectric constant. This is the capacitance in case of when you have the dielectrics placed in parallel. Guys, let me know in the live chat if this is clear to each and every one. Guys, let me know in the live chat if this is clear to each and every one. C is equal to epsilon naught D, epsilon naught by D, A1 by A1 into K1 plus A2 into K2 plus A3 into K3. Guys, is everything, or I am confusing you? Is it getting clear, crystal clear, or I am confusing you? I just need to know, guys. I just need to know. Okay. And if somebody asks you to find here, to find K equivalent in parallel combination. Sir, here, these are connected in parallel. These dielectric slabs are placed in parallel. So over here, if somebody asks you to find their net dielectric constant or K equivalent or equivalent dielectric constant, we say that is nothing but K equivalent is nothing but, simply remember, sir, A1 into K1 plus we say A2 into K2 plus we say A3 into K3, and then you divide it with simply that is nothing but, we say over here, that is nothing but over here with this D. Okay, simply as simple as that, as simple as that. Okay, I hope this is clear to each and every one. Okay. Sorry. This is not D over here. This is A. Where A is the area of plates. Where A is the area of plates. Sir, what is A1? A1 is the width of this one. A2 is this one. So equivalent dielectric is nothing but A1 K1 plus A2K2 plus A3K3 upon this A. Okay, I hope this is clear to each and everyone. Cool. So when you have the dielectric slabs placed in parallel, in that case, this is the equivalent capacitance. And if you have to find the equivalent dielectric constant, that is equal to A1K1 plus A2K2 plus A3K3. What is A1? A1 is the width of the dielectric first, and A2 is the width of second dielectric, A3 is the width of third dielectric upon A. A is the area of plates. Okay, cool. Now, this is the question which I wanted to exactly show you. Before this, I want to show you this question. Now, see, this is the question. I hope this is visible. In this particular case, we are given a parallel plate capacitor. This is a parallel plate capacitor in which two dielectrics are placed. One is air and another is this K. And you have to find the net capacitance of this one. To find C equivalent, or we say, sir, new capacitor. See, if between the plates you have placed two dielectrics, can you guys tell me in this particular case, these two dielectrics, air and K, are they placed? This is having the width of A2, this is having the width of A2. Are they A by 2? Are they placed in parallel or series? I just need to know in the live chat. Guys, I just need to know in the live chat. Are they placed in series or parallel? These two dielectrics, air and K, are they placed in series or parallel? Everyone. I want every one of you to answer this particular question in the live chat. Great. Now, we have to find its equivalent capacitance. How to find the equivalent capacitance when dielectrics are placed in parallel? Sir, we use this formula. Epsilon naught by D, A1K1 plus A2K2 plus A3K3. So we'll be using the same formula. Sir, C is equal to epsilon naught by D. Then we have, sir, A1K1. Then we have plus A2K2. Then we have plus A3K3. Sir, we say, sir, this C is equal to epsilon naught divided by D. Okay. Now in this case, A1, what is the value of A1? Sir, A1 is A by 2. So we say, sir, this is A by 2. Okay. And then what is the value of K1? Sir, K1 is air. So value of K is 1 in case of air. So this will be 1. Then plus A2. What is the value of A2 over here, sir? That is also A by 2. Into, sir, what is the value of K2? That is, sir, K in this particular case. Now we can further simplify this. This is epsilon naught divided by D. Then you have C. In this case, A by 2. We can take it common. So this will be A divided by 2. So what remains? This will be 1 plus this is K. Now see, epsilon naught A by D. This is C dash, new capacitance. Okay. To find new capacitance, C dash. Epsilon naught A by D. Sir, epsilon naught A by D is the capacitance when no dielectric is placed between the plates. So that is C. So we say this will be C dash. Instead of epsilon naught A by D, we say, sir, it is C. And then you have divided by this 2. Epsilon naught A by D. Instead of this, we write C by 2. Then you have 1 plus K. 1 plus C by 2, 1 plus K. Option 1. Yes, option A. Great. Now, can you solve this question? This was the question, one of the best questions I can see in this category. So this was the question which was asked in NEET 2020. See, you guys are supposed to tell me in this particular case, we have the two plates, okay? Now over here, one dielectric K1, another K2, another K3 and K4. 4 dielectric slabs are placed in series as well as parallel. Now see over here. And you guys are supposed to tell me K equivalent. That is a net equivalent dielectric constant. You will say, sir, in order to find the equivalent dielectric, we have to just first find them in series. In series, we have to use the formula. Then in parallel, we have to use the formula. It becomes complicated. Yes. So I'll show you the trick over here in this question. I'll show you the trick in this question. Let me show you. See, you don't have to see. This slab, this slab, this slab. You'll say, sir, and this slab. All these are in series parallel. You don't have to use those formulas to find the answer over here. What you will do is that, let's suppose if I say, if we say K1 is equal to 1. What does that mean? If I say this dielectric slab is made of air, this is an air. So for air, we say K1 is 1. And if I say K2 is also 1, over here we say K2 is also air. Then we say, sir, over here K3 is also 1 and K4 is also 1. I am assuming if this is 1, 1, 1, 1, means if all of the values are 1 over here, means air is placed in between this. Yes. Now, in that particular case, if all of these are 1, can I say, sir, K equivalent has to be 1 also? Yes. In that case, K equivalent has to be equal 1 also. Yes. Why? Because if this is air, this is air, this is air, this is air. So means their equivalent. Equivalent of air is air. As simple as that. So we say then K equivalent has to be equal to 1 also. Yes, I can say. Now, these are the 4 options. Among these 4 options, you have to check if right hand side is equal to the left hand side. That is your correct option. That is your correct option. Let's check for first option. What does first option say? First option says this one. That is K. Let's check for first option. Let me show you over here. K is equal to K1 plus K2 plus K3 plus, we say that is 3 times of K4. 3 times of K4. We are saying, sir, K1 is 1. 1 plus 1 plus 1 plus 3 into 1. So this is 3 plus 3 is 6. So K is equal to 6. No, K has to be equal to 1. As simple as that. Or LHS has to be equal to RHS. Let's check for this option. Let's check for option C directly. Now see, option C is 2 by K. Option C. Option C. That is 2 divided by K is equal to. This 2 by K is equal to 3 upon K1 plus K2 plus K3. 3 upon, we say K1 plus K2 plus K3. And then you have plus 1 by K4. Plus 1 by K4. Now see in this particular case. If I say, sir, this is 2 upon K is equal to. Sir, this will be 3 upon. What is the value of K1? We are assuming this 1 plus 1 plus 1 plus 1 upon. What is the value of K4? This is also 1. So 3 divided by 3 is 1 plus 1. So this is 2 divided by K. Okay, this is 3 by 3. 3 by 3 is 1 plus 1 by 1 is 1. 1 plus 1 is 2. So this will be 2. LHS is 2. This is 2. And now, so can we say over here in this particular case, so K divided by, in this particular case, we have to assume this K also as 1. Because if all will be 1, this will be also in this case will be exactly 1. So K is also equal to 1 over here. Just place this K also as 1. So this will be 1. So this will be 2 by 1 is equal to 3 by 3 plus 1 by 1. So this is 1, 1, 2 by 1. So 2 by 1 is equal to 2 by 1. LHS is equal to RHS. So it means option C is the correct option. Okay. Option C is the correct option. Is it clear, guys? Is it clear? Is it clear? You have to check. Yes. Okay, I'll explain once again. See, what I'm trying to say is that if you place K is equal to 1, K2 is equal to 1, K3 is equal to 1, K4 is equal to 1, means this is air. So their equivalent is also air. means K equivalent is also 1. For air, K is equal to 1. Yes. Now check, this is K equivalent, this is K equivalent, this is also K equivalent. If you say, sir, K1 is 1, K2 is 1, K3 is 1, K4 is 1. And you say, sir, K equivalent will be also 1. So if you are placing this is 1, so this should also be, this should also be equal to 1. So if LHS becomes equal to RHS means this is the correct option. But in the first case, we didn't get it. But in the second case, I'll show you once again. I'll show you this case once again. Let me show you over here. See, you are saying, sir, this is the option you have over here in this case. This is the option. Sir, this is K equivalent. You are saying if K1 is 1, K2 is 1, K3 is 1, K4 is 1, K equivalent has to be equal to 1 also. Yes. So we say 2 upon K equivalent is 1 is equal to 3 upon K1 is 1 plus K2 is also 1, K3 is also 1, then plus 1 upon K4 is also 1. So this is 3 upon 3 is 1. So we say 3 divided by 3 plus 1 by 1. This is 2 by 1. So then you can further write it over here. Sir, this is 2 divided by 1 is equal to 3 by 3 is 1. 1 plus 1 is 2. So this is also 2 by 1. 2, 2 means LHS is equal to RHS. This is the correct option. This is matching. If you are not getting this, leave it. As simple as that. Leave it, leave it, leave it. Okay. Now we have the combination of plates. We have the combination of plates. It will take us, we'll get done at 10 o'clock. Okay. 10 o'clock we'll finish this entire chapter. Yes, you can do this. You can use this technique. Even in the next question, in this question also, you can use the same technique. Even in this question, you can use the same technique and you can get the answer. Okay. Now you have combination of parallel plates. What does the combination of parallel plates mean? Listen to me very carefully. Let's suppose we have, if this is visible, yes, we have 3 plates. This is the first plate you have. This is the second plate and this is the third plate. So we say over here, 3 plates are placed in parallel to each other. 3 plates are placed parallel to each other. So we say, sir, how many plates form one capacitor? We say 2 plates form one capacitor. This is the first plate. This is the second plate. Okay. 2 plates form one capacitor. Now over here, sir, this plate and this plate, they form one capacitor. And this plate, they form another capacitor. Means we have 3 plates placed parallel to each other. So they form, we say 2 capacitors. They form 2 capacitors. So 3 plates are placed parallel to each other. So they form 2 capacitors. One capacitor is this one, another capacitor is this one. Now we have to draw it over here. Draw these capacitors, capacitors. Listen to me very, very, very carefully. How do we draw these capacitors? Let's suppose we say, sir, this plate, this middle plate is connected to the point X. And this left one is connected to the point Y. This right one is also connected to the point Y over here. Now, listen to me very carefully. Sir, this plate is connected to the point Y. This plate is connected to the point X. How many points are mentioned over here? You say, sir, only 2. First is X and another is Y. Can you guys tell me, this first capacitor is connected between which point? You say, sir, X and Y. So you'll make it over here. This is between X and Y. Can you tell me, this next capacitor is connected between which point and which point? You say, sir, X and this is Y because this is connected to Y. So it will be also over here. So now this capacitor has capacitance C, it has C. How much is the equivalent capacitance? They are in parallel. We say equivalent capacitance is 2C. Is this clear? Is this clear what I'm trying to show in this one? Over here, 3 plates are placed parallel to each other and we have to find their net capacitance. We have to find their net capacitance. I hope this is clear to each and everyone. Let's move on to the next one. Now, in this particular case, we have 1 plate, second, third, fourth. This plate is connected to X, this is connected to Y. First, find the number of capacitors formed and find net capacitance. Find net capacitance in this case and find the number of capacitors formed over here. Can you guys tell me the number of capacitors formed in this case? Number of capacitors formed and net capacitance in this particular case. See, this plate is connected to X, this plate is connected to Y. Let's suppose this plate is connected to the fourth plate. Okay, first is connected to the 4 with the help of a simple wire. Let's mention one more point, that is P. Now, how many points? See, this plate is connected to P, so this plate is also connected to P. Now, how many points are over here? P, X and Y. Mark these points, sir, X, then you say P, and then you say, sir, Y. Okay. Now, first capacitor is connected between P and X. So we say we'll make it over here. Sir, these 2 plates form 1 capacitor, second capacitor between this and this is third capacitor between this and this. So 4 plates form 3 capacitors over here. Great. Now, first one is connected between P and X. I'll make it between P and X. Second is connected between X and Y. So it will be something like this between X and Y. So let's say it has capacitance C, it has capacitance C. Third is connected between Y and P. See, this plate is connected to Y, this is P. So this is between Y and P. So this is C. I hope this is clear to each and everyone. I hope this is clear. Yes. Now in this case, boys and girls, listen to me. Listen to me very carefully. You have to find the net capacitance. Sir, this capacitor and this capacitor, they are in series. Now, C and C, when they are in series, sir, C equivalent of this one. So C equivalent will be C1, C2. When you have 2 capacitors in series, how do you find the C equivalent? C1, C2. You say, sir, C into C, C1, C2 upon C1 plus C2. That is C square by 2C. This will cancel C by 2. So answer is C by 2. Now, the equivalent of this and this, the equivalent of this one and this one is C by 2. So I'll make it over here. This is C by 2 and then this is nothing but C. This is C by 2, this is nothing but C. Okay. Now this C by 2 and this C by 2 are in series. So they will have C equivalent of, we say, sir, C divided by 2 plus C. Because they are in series. Okay. So C equivalent will be, that is 2 into C is 2C plus C, that is 3C divided by 2. How many of you got 3C divided by 2? How many of you got 3C divided by 2? First, these 2 are in series. They are in series. Okay. When you find their equivalent, they have C by 2 equivalent, C by 2. Then this C by 2, instead of this C by 2 and this C by 2, they are in parallel. So their equivalent capacitance will be C by 2 plus C, that is 3C by 2. Is it clear, guys? I just need to know. Got it, everyone, everyone. Let's move on to this one. Okay, tell me about this one. Here we have 4 plates. So 3 capacitors will be formed. This plate is connected to A, this plate is connected to B. So let's mark the point P over here. If this is point P, so this is also point P, because they are connected. They are connected by means of a simple wire. They are connected by means of a simple wire. Okay, they are connected by means of a simple wire. Now, in this case, we have to find the equivalent capacitance. See, 1 and 2 will form one capacitor, first capacitor. 2 and second and third plate will form another capacitor. Third plate and fourth will form another capacitor. This is the third capacitor. Okay. Now in this particular case, mark the points, sir. First one is A, second one is P, another one is B. Now first capacitor is connected between A and P. See these two plates, A and P. Let me make it over here. Let's say this is C. Sir, next capacitor is connected between A and this is also P. So let's connect it something like this. So this is C. Sir, third capacitor is connected between P and B. Let's make it something like this. This is C. Now these two are in series. These two are in series. Sorry, parallel. These two are in parallel. So they will have the equivalent of 2C. C plus C is 2C. So I can make it something like this. This will be 2C. And this C is nothing but in series. Now this C, 2C and this C, they are in series. So their C equivalent will be C1 C2 upon C1 plus C2. C1 is 2C, C2 is C upon 2C plus C. So this is 2C square upon 3C. This and this will get cancelled. 2 by 3C. How many of you got 2 by 3C? Let's move on to the next one. Okay. Can you tell me what is the net capacitance in this case? Sir, we have got, this is the first plate, this is first plate, another plate, another plate, another plate. Now, over here, if I mark the points, sir, this is point A. So this point A means, this is also point, this is connected to point A. So means this is simple wire, this is also connected to point A. Sir, this is point B. So means this is connected to point B, and over here this is connected to point B. Now, listen to me very carefully in this case. Listen to me very carefully. Listen to me very carefully. Means this is point A and this is point A. This is point B, this is point B. Now see, sir, this is the first capacitor, this plate and this plate. Between these two plates, this is the first capacitor. This is the second capacitor and this is the third capacitor. Now, how many points are over here? A and B. So we say A and this is B. First capacitor is connected between, sir, this plate is A, this is B. Between A and B, let me make it over here, this is C. Second capacitor is connected between B and B. Shall I remove the middle capacitor? Why? Because it will short circuit, because it is connected between same points B and B. So it will short circuit. Okay. And then third capacitor is connected between A and B. This is connected between A and B. Okay. Now what is the C equivalent in this case? You say, sir, C plus C is nothing but 2C. Next you have this one. Okay. Now see, this point is over here, sir, A. And then if you take this route and you will reach over here, this is also A. This point is, sir, B. And if you take this route, this will be also B. Yes, yes. Now, can you tell me how to find in this particular case, the net capacitance? See, first and the foremost thing, C, three capacitors are in series. So what will be their equivalent capacitance? We say, sir, their equivalent capacitance will be C by 3. Okay. If you find their equivalent capacitance, that will be C by 3. Don't add them. It is 1 by C equivalent is equal to 1 by C1 plus 1 by C2. So it will be nothing but C by 3. Mark the points A and this is B. Now see, first, these capacitors, their resultant, their equivalent will be C divided by 3. So that C by 3 is connected between what? A and B. And the next one, this capacitor, this is also connected between A and B. So this will be also C between A. These three capacitors, see what I'm trying to say over here is, you have three capacitors. So find their equivalent, that is C by 3. That is connected between, that C by 3 is connected between A and B. So we say between A and B, this C by 3. And this last capacitor is connected between A and B. So I'm making it over here. Now find the C equivalent in this case, we'll get the answer. Okay, can you solve this particular question? Can you solve this particular question? See, let's suppose this is the point X over here at the center. Let's suppose this is the point Y over here. If this is point Y, sir, we have got one capacitor, second, third, fourth. We have to find equivalent capacitor. If this is Y, can I say, sir, this will be also Y because the wire is simple wire till over here? Then can I say this is also, sir, Y, and can I say this is also Y? Now, if you see over here, all the capacitors are connected between X and Y. This is 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 between X and Y. Okay? Okay. Now, here, all the capacitors are connected between X and Y. Now see, let me draw X and this is Y. Let's draw the first capacitor. Sir, this capacitor is connected between X and Y. So we say this is the first one. This one is also connected between X and Y. So we say this is C. This one is also connected between X and Y. We say, sir, this is C. This is also connected between X and Y. We say C. So C, 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 all four. So we say, sir, C equivalent will be nothing but 4C because C1 plus C2 plus C3 plus C4. Yes, great, 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 great. This is your homework. Okay. You have to find you have to find the net capacitance in this case also. Wheatstone bridge. Wheatstone bridge. This is the last concept. Now see, I'll tell you. Let's suppose I have a capacitor over here. I have a capacitor over here. I have one more capacitor over here. I have one more capacitor over here. I have one more capacitor. This is C1. This is C2. This is C3. This is C4. This is C5. I have a combination of this type, of this sort. I am asking you the simple question. Find net capacitance in this system, in this circuit, you say, in this combination circuit. You guys are supposed to tell me what is the what is the net capacitance? What is the net capacitance in this system? You guys are supposed to tell me what is the net capacitance? What is the net capacitance in this case? What will you do? Sir, we'll take these two in series first. Then we'll do in parallel. No, sir. This one and this one, they are not in series. Why? Because the middle capacitor is connected over here. Even if I give you the value, this is C, this is C, this is C, this is C, this is C. Still, it is impossible for you to solve this type of circuit. It becomes very, very, very complicated. So we say this is a Wheatstone bridge. This is a Wheatstone bridge. Whenever you see something like this, it's a Wheatstone bridge. Now, in this Wheatstone bridge, in order to find the equivalent of this one, now see, what we do is that we say according to Wheatstone bridge concept, according to Wheatstone bridge concept, it says if this capacitance C1 divided by this capacitance C2 is equal to this capacitance C3 divided by this capacitance C4. Let's suppose I say this C, this is C. So C by C is equal to, this is also C, this is also C, C by C. Then remove C5 because no charge will be stored in C5 or no charge flows through C5. What does that mean? Sir, Wheatstone bridge says if this capacitance divided by this capacitance is equal to this capacitance by this capacitance, then you can remove the middle capacitor. You can remove the C5. Why? Because in that case, no charge is stored in C5. If no charge is stored in this capacitor, means it is of no use, we can remove it. So if we remove it, we can make it something like this afterwards. We can make it something like this afterwards. So this is C1, this is C2, this is C3, this is C4. Now can you solve this? If I say C1 is C, if I say this C1 is C, this C2 is C, C3 is C, this C4 is C, this is C, this is C, this is C, this is C. Can you solve this? Yes, it is very simple now. Sir, how? Sir, now we say, sir, these two are in series, these two are in series, these two are in series. So resultant or net equivalent of this one and this one, C and C, it will be C by 2. When you find their equivalent in series, that is 1 upon C equivalent is 1 by C1 plus 1 by C2. It is C by 2. How, sir? I'll tell you. C equivalent is C1 C2 upon C1 plus C2. C1 is C into C2 is C upon C1 plus C2. Sir, this is C square by 2C. This and this, it will be C by 2. It will be C by 2. Okay. So that's what I said. Equivalent of this and this is C by 2. And equivalent of this is also C by 2. Now we can make it something like this. One capacitor is C by 2. Another capacitor is C by 2. This is C by 2. This is C by 2. Now equivalent is when the two capacitors are in parallel. We say, sir, equivalent is C1 plus C2. So it is C by 2 plus C by 2. That is equal to C. So equivalent of this becomes C. So you were only able to solve this when you applied the concept of Wheatstone bridge. So that's why the concept of Wheatstone bridge says if C1 by C2 is equal to C3 by C4, then we say we can remove C5, remove C5. So it becomes very simple then. It becomes very simple then. Let's suppose if you have this particular question. If you have this particular question over here, can you solve? Find C equivalent. If C1, C2, C3, C4 are C. If all the capacitors are having the capacitance as C, you'll say, sir, simply, sir, it is a Wheatstone bridge. Wheatstone bridge. Wheatstone bridge. Sir, how it is a Wheatstone bridge? I'll show you. Sir, over here, if you just take a look at this C1, see, I can make it something like this. I can make it something like this. This is C1. And I'll make it something like this. This is C2. And this is X over here. This is XO. I'm redrawing the circuit. This is C1. This is C2. Then you have C3 over here. This is, sir, C3. Then you have C4 over here. This is C4. And this is, sir, point Y. And in between is this middle resistor. That is C5. Don't you think it is exactly like what? The Wheatstone bridge, 110%. Now in this particular case, we say, sir, C1 by C2, if all are C. So we say here C1 by C2 is equal to C3 divided by C4. Then we can say remove C5. If we remove C5, means then we can find the equivalent, and that is exactly similar to this one. And answer will come out to be C. Is this clear, guys? Is this clear? Is this Wheatstone bridge clear? Wheatstone bridge simply says if C1 by C2 is equal to C3 by C4, then remove the middle one and solve that circuit by series parallel method. Is this clear, guys? Each and everyone, we are done with the session. I'm going. Let me know in the live chat. And this is the last question. This is your homework. Comment down the answer. Okay. And most importantly, how was the session? If you like the session, do let me know in the comments down below. Don't forget to like this video and share this session. Do let me know in the comments down below. Okay, each one of you, I want all of you to let me know if okay. Mouse करा लो. Okay, great. I want you guys, once I end the stream, I want you guys to let me know in the comments down below how was the session and everything. Thank you so much. It was all about it. Okay, guys, take care and bye bye.